The Bootstrap Paradox. Information from nowhere. A scientist builds a time machine. Into it, she places a notebook containing the complete plans for building that very time machine. She sends this notebook back in time 30 years, where her younger self discovers it. This younger version studies the notebook, follows its instructions precisely, and eventually builds the identical time machine that will, decades later, send that same notebook back in time. Here's the question that shatters causality. Who designed the time machine? Who wrote the notebook? The information seems to exist in a perfect loop, with no point of origin, bootstrap lifting itself into existence from nothing. This is the bootstrap paradox, also known as a causal loop or ontological paradox, a situation where information or objects exist without ever being created. The item or knowledge loops through time, creating itself through a circle of causation with no discernible beginning. While fictional time travelers worry about stepping on butterflies or meeting their grandparents, this paradox suggests something far more disturbing. The fundamental laws of causality might be more flexible than we ever imagined. The controversy surrounding this paradox has divided physicists, philosophers, and science fiction enthusiasts for decades. Some argue that such loops are logically impossible, violating fundamental principles of causality, where effects must follow causes. Others suggest that if time travel is possible at all, bootstrap paradoxes might be not just possible but inevitable, the universe's way of maintaining consistency in the face of timeline manipulation. Consider the deep implications. Our entire understanding of reality assumes linear causation, where causes precede effects. What happens to physics, to logic, to our very conception of reality, if this assumption proves false? If information can exist without being created, what does this suggest about the nature of information itself? Perhaps information isn't just a product of physical processes, but something more fundamental, possibly even more fundamental than matter or energy. The paradox becomes even more unsettling when applied to artistic creation. Imagine a musician who's inspired by a melody she hears on the radio. Years later, she travels back in time and plays that very melody, which is recorded and eventually broadcast, inspiring her younger self. Who composed the melody? It seems to exist in a creative vacuum, an artistic immaculate conception with no genuine creator. Does creativity itself require an original moment of inception, or can artistic works bootstrap themselves into existence? Some physicists suggest the paradox reveals something profound about the nature of time itself. Perhaps our intuition that time flows linearly from past to future is merely a persistent illusion, a limited perspective imposed by our three-dimensional existence. From a four-dimensional perspective, where time is just another dimension like length or width, causal loops might appear perfectly natural, not paradoxes at all, but mere geometric features in space-time's complex topology. The implications for free will are equally disturbing. If you obtain knowledge from your future self, and then inevitably become that future self who delivers the knowledge, was any choice ever involved? The loop seems to lock participants into a predetermined sequence, creating a fatalistic trap where free will is merely an illusion. Yet quantum mechanics suggests reality contains fundamental indeterminacy. Can these perspectives be reconciled, or does time travel necessarily collapse quantum possibilities into singular, fixed timelines? Some versions of the paradox involve physical objects rather than information. A watch that's given to a young man by a mysterious stranger, which he later in life takes back in time to give to his younger self. This version raises even more troubling questions. The watch never seems to be manufactured, yet exists physically. Does it age? Does it deteriorate over time? If so, how can it exist indefinitely in the loop? If not, does it somehow violate the second law of thermodynamics? The paradox challenges our understanding of information theory and entropy. Physical objects inevitably deteriorate over time as entropy increases. An object caught in a temporal loop would seemingly experience unlimited time, yet must remain stable enough to complete the loop repeatedly. This suggests either a violation of thermodynamic laws or additional complex mechanisms to reset the object's state with each loop iteration. Either way, fundamental physical principles seem to strain under the paradox's weight. Some theorists propose that bootstrap paradoxes might be impossible in our universe precisely because they violate conservation laws. Information and physical objects cannot emerge from nothing. The energy and matter must come from somewhere. Perhaps the universe has built-in safeguards that prevent such paradoxes, making certain types of time travel inherently impossible, or redirecting time travelers into parallel timelines to avoid causal violations. Others suggest a quantum perspective might resolve the paradox. In quantum mechanics, particles can appear to influence their own past states through retrocausality. Perhaps bootstrap paradoxes operate similarly. The future event doesn't cause the past event in a traditional sense. Rather, they mutually constrain each other across time in a more complex causal relationship. The notebook isn't created by either the younger or older scientist, but emerges from their interaction across time itself. The notion of self-causation extends beyond time travel scenarios into metaphysics and theology. Some philosophical traditions describe God as a self-caused being, existing necessarily without prior cause. The bootstrap paradox raises similar questions about whether anything can truly cause itself, or whether all causation requires an external initiator. Perhaps the paradox reveals fundamental limitations in how we conceptualize causality itself. The paradox becomes even more complex when we consider consciousness and memory. If you receive information from your future self, then later deliver that same information to your past self, whose idea was it originally? The thought seems to exist in your mind across time, but without a moment of conception. This challenges our understanding of creativity and inspiration. Are all ideas ultimately received rather than generated? Modern physics offers tantalizing hints that causal loops might be more than mere thought experiments. In quantum field theory, virtual particles can appear to travel backward in time, as positrons, for example. Closed time-like curves, theoretical pathways through space-time that return to their starting point, appear in some solutions to Einstein's field equations. While these don't confirm the possibility of bootstrap paradoxes, they suggest our universe might not prohibit them entirely. The next time inspiration strikes seemingly from nowhere, consider the bootstrap paradox. Perhaps your brilliant idea wasn't created in that moment but received, passed to you from across time, possibly even from your future self. Perhaps causality isn't the one-way street we've always assumed, but a complex network where effects sometimes precede causes, and information sometimes creates itself. The notebook containing the time machine plans raises questions without answers, paradoxes without resolutions. It reminds us that even our most fundamental assumptions about reality, that everything must have a beginning, that information must be created, that effects must follow causes, might be merely limitations of human perspective rather than universal truths. In the face of the bootstrap paradox, certainty itself begins to unravel. The unexpected hanging paradox. When knowledge destroys itself. A judge sentences a prisoner to be hanged at noon on one of the 7 days of the coming week. But there's a twist. The execution will be a surprise. The prisoner won't know which day until the morning of the hanging. The prisoner, a logician by training, begins to reason. It can't be Sunday, he concludes, because if I haven't been hanged by Saturday night, I would know with certainty that Sunday is the day, which would violate the surprise condition. With Sunday eliminated, he continues his reasoning. It can't be Saturday either. If I reach Friday evening unhanged, and I've already eliminated Sunday, I would know with certainty that Saturday must be the day, again violating the surprise condition. He applies this logic repeatedly, eliminating Friday, Thursday, Wednesday, Tuesday, and finally Monday through the same reasoning. Satisfied, he returns to his cell, confident that the hanging cannot occur. Yet when Wednesday arrives, the guards come for him. As he's led to the gallows, he realizes with genuine surprise that he's being hanged on Wednesday. The judge's decree is fulfilled exactly as stated. A hanging on one of the 7 days, completely unexpected until the morning it occurs. This is the unexpected hanging paradox, also known as the surprise examination paradox, a devilish logical puzzle that has confounded philosophers, mathematicians, and logicians since its first formulation in the 1940s. Its elegant simplicity masks profound questions about knowledge, prediction, and the limits of logical reasoning itself. The controversy surrounding this paradox has divided thinkers into competing camps. Some argue it reveals fundamental limitations in self-referential logical systems. Others suggest it demonstrates the distinction between different types of knowledge, knowing something as a logical truth versus knowing it as an experienced fact. Still others believe it hinges on the paradoxical nature of surprise itself. How can an event be both predicted and surprising? Consider the prisoner's fatal error. His logical elimination process assumes that knowledge is cumulative and unchanging, but the very act of reasoning changes what he knows. His conclusion that the hanging cannot occur becomes part of his knowledge base, which then makes any hanging genuinely surprising. The paradox creates a strange loop where the prediction of an event affects the conditions that make the prediction valid. Some philosophers compare this to quantum mechanics' observer effect, where the act of measurement changes the system being measured. The prisoner's reasoning doesn't just describe reality, it alters it. His knowledge isn't separate from the system he's analyzing, but is itself a variable within that system. This self-referential quality creates the logical instability that makes the paradox so resistant to resolution. The paradox becomes even more complex when we consider its implications for epistemology, the philosophy of knowledge. What does it mean to know something will happen? If I predict an event with perfect logical certainty, but am still surprised when it occurs, did I really know it would happen? Perhaps the paradox reveals that different types of knowledge, logical, anticipatory, experiential, cannot be perfectly reconciled within a single framework. Some logicians focus on the temporal aspects of the paradox. The prisoner reasons about his future knowledge states from his present knowledge state, creating a complex web of nested beliefs about beliefs. Perhaps our logical systems simply aren't equipped to handle these recursive temporal projections correctly. The paradox might reveal the limitations of applying atemporal logic to temporally unfolding scenarios. The implications extend far beyond abstract philosophy. Consider financial markets, where predictions about future prices affect current trading behaviors. which in turn affect future prices. A widely believed prediction about a market crash can trigger the very crash it predicted, or prevent it entirely. This self-referential quality makes precise market prediction inherently paradoxical, similar to the unexpected hanging's logical structure. Or consider public health warnings. If authorities predict a severe pandemic and implement preventive measures that successfully mitigate it, the public may conclude the prediction was exaggerated, precisely because the warning was taken seriously. The success of the prediction undermines belief in its accuracy, creating a paradox for public communication of risks. Some philosophers have suggested that the paradox reveals a fundamental distinction between self-fulfilling and self-defeating prophecies. The prediction that a hanging cannot occur is self-defeating. Once believed, it creates conditions, surprise, that make the hanging possible. Understanding which predictions undermine themselves when believed might be key to resolving certain types of paradoxes. Others focus on the nature of surprise itself. Surprise requires both an expectation and a violation of that expectation. But can one legitimately expect something while simultaneously expecting to be surprised by it? This creates a strange loop in our cognitive processes. I expect X to happen unexpectedly, but if I expect it, it won't be unexpected. So I don't expect it, which means it would be unexpected, so I do expect it, and so on in an infinite regression. The paradox becomes particularly troubling when applied to mortality. We all know with logical certainty that we will die, yet this knowledge doesn't prevent death from being surprising when it arrives. Perhaps certain truths cannot be fully integrated into our expectational framework, remaining perpetually unexpected, despite being logically certain. Our mortality might be the ultimate unexpected hanging, known yet never truly anticipated. Some mathematicians have approached the paradox through modal logic and possible world semantics. They distinguish between what is known in all possible futures versus what is known in the actual future that unfolds. The prisoner's error, they suggest, is conflating these different types of knowledge, mistaking what must be true in all possible worlds for what will be true in the actual world. The paradox also relates to Gödel's incompleteness theorems, which demonstrate that any consistent logical system complex enough to describe basic arithmetic must contain statements that are true but unprovable within that system. Perhaps the statement, "the hanging will occur surprisingly on day X," is similar, a proposition that cannot be proven or disproven within the logical system available to the prisoner. The next time you find yourself absolutely certain about a future event, remember the unexpected hanging. Remember that your very certainty might change the conditions that made your prediction seem inevitable. Remember that knowledge isn't just a description of reality, but an active force within it, capable of creating the very surprises it attempts to eliminate. The condemned logician, walking to the gallows on Wednesday, learned the hard way that perfect reasoning doesn't guarantee correct conclusions when the reasoning itself changes the system being analyzed. Perhaps true wisdom isn't perfect prediction, but understanding the limits of prediction itself, especially when we ourselves are variables in the equations we're trying to solve. The Saint. Petersburg Paradox. When infinite value meets finite reality. Imagine being offered a game with the following rules. A fair coin is tossed repeatedly until it lands on tails. If the first toss comes up tails, you win $2. If tails appears on the second toss, you win $4. If on the third toss, $8. Each additional flip before tails appears doubles your potential payout. The question that has perplexed mathematicians, economists, and philosophers for centuries is disarmingly simple. How much would you pay to play this game? The paradox emerges when we calculate the expected value, the probability-weighted average of all possible outcomes. The probability of tails on the first flip is 1/2, giving an expected value contribution of 2 times 1/2 equals $1. The probability of heads followed by tails is 1/4, contributing $1, $4, times 1/4 equals $1 to the expected value. Heads, heads, tails occurs with 1/8 probability, adding 8 times 1/8 equals $1. This pattern continues infinitely, with each scenario contributing exactly $1 to the expected value. With infinitely many possibilities, the game's mathematical expected value is infinite. Standard economic theory suggests a rational person should be willing to pay any finite amount to play a game with infinite expected value. Yet practically no one would pay even $100 for the opportunity. This stark contradiction between theoretical rationality and actual human behavior is the St. Petersburg paradox, first analyzed by Swiss mathematician Daniel Bernoulli in 1738. Its elegant mathematical formulation masks profound questions about rationality, valuation, and the psychology of risk that continue to challenge our understanding of decision-making under uncertainty. The controversy surrounding this paradox has divided economists, psychologists, and decision theorists into competing camps. Some argue it reveals fundamental flaws in expected value as a decision criterion, suggesting we need more sophisticated utility models that account for risk aversion. Others maintain the paradox demonstrates practical constraints on theoretical rationality, from the finite wealth of potential players to the physical impossibility of truly infinite games. Still others see it as exposing a fundamental mismatch between mathematical idealizations and embodied human decision-making. Consider the profound implications. If human behavior systematically diverges from theoretical rationality in this simple game, how many other economic theories based on similar rationality assumptions might be fundamentally misaligned with actual human behavior? The paradox challenges not just how we value uncertain outcomes, but the very foundation of rational choice theory that underlies much of economics, finance, and policy analysis. Bernoulli himself proposed one resolution through the concept of diminishing marginal utility, the idea that each additional dollar provides less satisfaction than the previous one. Under this framework, the utility of potential winnings grows more slowly than their monetary value, eventually making the expected utility finite, despite infinite expected monetary value. This insight laid the groundwork for modern utility theory and risk analysis, demonstrating how seemingly irrational behavior might actually reflect sophisticated psychological valuation mechanisms. Others focus on practical limitations. Real-world constraints make truly infinite payouts impossible. No casino has infinite funds, and no coin can be flipped infinitely many times. Even the wealthiest entities on Earth could only sustain the game for about 30 to 35 flips before exhausting all available resources. Perhaps our intuitive unwillingness to pay large amounts reflects an implicit understanding of these practical bounds, making our behavior more rational than it first appears. The paradox becomes even more fascinating when we consider its psychological dimensions. Studies show humans systematically underweight unlikely events with large consequences, precisely the scenario in the St. Petersburg game, where enormous payouts occur with vanishingly small probabilities. This possibility neglect appears in many contexts, from insurance decisions to lottery participation, suggesting the paradox reveals fundamental features of human probability processing rather than irrationality. Some mathematicians propose that the paradox exposes conceptual difficulties with infinity itself. While mathematical infinity is well defined, human decision-making evolved in contexts where truly infinite quantities never appear. Perhaps our intuitions break down when confronting genuinely unbounded quantities, making the paradox less about rationality and more about the limitations of applying infinite concepts to practical decision-making by finite beings. Financial theorists have found parallels between the St. Petersburg paradox and modern investment dilemmas. Certain investment strategies theoretically offer infinite expected returns, given infinite time horizons, yet practical investors still limit their exposure. The paradox helps explain why markets don't behave according to simple expected value calculations, and why risk management remains essential despite theoretical arguments for extreme positions in certain assets. More recent approaches connect the paradox to complexity and computational limitations. Calculating expected values for exotic probability distributions requires sophisticated mathematical reasoning that exceeds natural human cognitive capacities. Perhaps our unwillingness to pay large amounts represents a rational heuristic given our computational constraints, a way of avoiding scenarios whose complexity makes accurate valuation practically impossible. The implications extend to artificial intelligence and decision theory. Should AI systems designed to make financial or safety-critical decisions follow expected value calculations, even when they diverge dramatically from human intuitions? The paradox raises profound questions about how we balance mathematical optimization against human values and intuitions in developing automated decision systems. Some philosophers argue the paradox reveals tension between different types of rationality: normative mathematical rationality versus ecological rationality, adapted to real-world constraints. While expected value calculations suggest paying enormous sums, ecological rationality, which considers resource limitations, computational constraints, and the structure of natural environments, might favor much lower valuations that align better with actual human behavior. The next time you face a decision involving small probabilities of enormous consequences, whether investing in a speculative asset, purchasing insurance, or considering a medical procedure with rare but severe side effects, remember the St. Petersburg paradox. Remember that mathematical expectation alone may offer an incomplete guide, and that your intuitive valuation might reflect sophisticated adaptations to real-world constraints rather than irrationality. The paradox teaches us that decision-making under uncertainty isn't merely about calculating probabilities and payoffs, but about navigating the complex interplay between mathematical idealization and practical reality. It suggests our intuitive approaches to valuation, though they may diverge from theoretical optimality, might embody a deeper wisdom about operating in a world where infinity exists in equations, but never in experience. The MORAVEC'S paradox. Why is the easy hard and the hard easy? In the early days of artificial intelligence research, experts predicted that the hard cognitive tasks requiring advanced reasoning, like playing chess or solving complex mathematics, would be the most difficult to automate. Meanwhile, the easy sensory motor skills that even toddlers master, like recognizing faces or manipulating objects, would be relatively simple for machines to replicate. Decades later, reality proved exactly the opposite. AI systems can defeat world champions at chess and Go, but still struggle to reliably identify objects or move through unstructured environments with the dexterity of a 5-year-old child. This unexpected reversal is MORAVEC'S paradox, named after robotics researcher Hans Moravec, who observed in the 1980s. It is comparatively easy to make computers exhibit adult-level performance on intelligence tests or playing checkers, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. The paradox reveals something profound about both human cognition and artificial intelligence. The capabilities we consciously value as uniquely human often prove most amenable to machine replication, while the fundamental skills we take for granted remain stubbornly resistant to automation. The controversy surrounding this paradox has divided AI researchers, cognitive scientists, and philosophers. Some argue it reveals fundamental limitations in our current computational approaches to intelligence, suggesting we need radically different paradigms to achieve general AI. Others see it as a temporary engineering challenge that will eventually be overcome with sufficient computing power and data. Still others believe it exposes something essential about the embodied nature of human intelligence, that our cognitive capabilities are inseparably grounded in our physical experience of the world. Consider the profound implications. Activities humans consider intellectually demanding, the abstract reasoning of chess grandmasters, the logical deductions of mathematicians, have proven relatively straightforward to formalize into algorithms. Yet the seemingly simple tasks of recognizing your grandmother's face, regardless of lighting conditions or picking up an oddly shaped object, remain surprisingly difficult for machines. What does this suggest about the true nature of human intelligence? Perhaps our most sophisticated cognitive abilities are merely recent evolutionary additions built atop far more complex foundations of perception and movement. The paradox becomes even more fascinating when we consider evolutionary history. Logical reasoning and abstract mathematics are recent human innovations, emerging only in the last few thousand years. But the sensory motor skills that AI finds challenging evolved over hundreds of millions of years, refined through countless generations of natural selection. Perhaps what we experience as intuitive or easy actually represents the most sophisticated capabilities of our nervous system. Processes so evolutionarily perfected, they operate below conscious awareness. Some cognitive scientists suggest the paradox emerges from how human knowledge is structured. The abstract reasoning we consciously perform relies on explicit knowledge that we can articulate and formalize into rules, but our perceptual and motor skills depend on implicit knowledge, neural processes refined through experience that operate outside conscious access. We can explain how to solve an equation, but struggle to explain how we recognize a face or maintain balance while walking. Machines excel with explicit knowledge, but flounder with the implicit. The implications extend beyond AI research into philosophy of mind and consciousness. If our highest cognitive functions prove most amenable to algorithmic replication, what does this suggest about human uniqueness? Perhaps consciousness itself represents a relatively thin veneer atop the true complexity of our embodied intelligence. The paradox challenges both our anthropocentric belief in the supremacy of abstract reasoning and our intuitive sense of which mental processes are truly sophisticated. The paradox becomes particularly relevant as we increasingly deploy AI in real-world contexts. Self-driving cars might handle highway navigation reasonably well, but struggle with the seemingly simple task of recognizing unusual objects or predicting pedestrian behavior. Medical diagnostic systems can outperform specialists in narrow tasks, but lack the holistic perception and intuition that experienced physicians bring to complex cases. Understanding the paradox helps explain why artificial intelligence often fails in unexpected ways when confronting the messy complexity of the physical world. Some researchers believe the solution lies in embodied cognition, the theory that intelligence emerges from the interaction between brain, body, and environment, rather than existing as abstract computation. From this perspective, trying to create disembodied intelligence through algorithms might be fundamentally misguided. Perhaps truly general AI requires physical embodiment and sensory motor experience similar to human development, learning through physical interaction rather than merely processing abstract data. Others focus on the different computational approaches required for different types of intelligence. Logical reasoning operates through serial processing with clear rules, making it well suited to traditional computing. But perception and movement require massive parallel processing of ambiguous signals with constant environmental feedback, capabilities that align better with neural networks and deep learning approaches. The paradox might reflect not the inherent difficulty of these tasks, but their poor fit with early computing paradigms. The implications extend to education and human development as well. If our most sophisticated capabilities are built atop unconscious perceptual and motor foundations, perhaps early childhood development of these physical skills creates the necessary neural substrate for later abstract thinking. This perspective challenges educational approaches that rush children into formal reasoning while minimizing physical play and sensorimotor development. The paradox suggests that abstract thinking doesn't replace embodied cognition, but depends on it. Modern AI developments have partially addressed the paradox through deep learning and neural networks, which have significantly improved machine perception capabilities. Yet even these systems, despite impressive advances, typically require far more training data than humans to achieve similar results, and often fail in unexpected ways when confronting novel situations. The gap between human and machine embodied intelligence, while narrowing, remains substantial. The next time you effortlessly recognize a friend's face in a crowd, catch a falling object, or navigate a cluttered room, remember MORAVEC'S paradox. Remember that these simple tasks represent the culmination of hundreds of millions of years of evolutionary refinement. Capabilities so sophisticated, they operate below your conscious awareness. Remember that what we experience as easiest is often what's most computationally complex, and what we prize as uniquely human may be what machines most readily replicate. The paradox invites a profound reevaluation of human intelligence, not as a pinnacle of abstract reasoning disconnected from our physical existence, but as an integrated system where our highest cognitive functions remain grounded in the rich complexity of embodied experience. It suggests that true intelligence isn't disembodied calculation, but the seamless integration of perception, action, and thought that we take for granted every moment of our lives. OLBERS paradox. Why is the night sky dark? Look up at the night sky. The darkness between stars seems unremarkable, expected, the natural backdrop for celestial bodies. Yet this apparent emptiness poses one of astronomy's most profound riddles. If the universe is infinite, eternal, and filled with stars, then every line of sight should eventually intersect a star's surface, making the entire night sky blaze as brightly as the sun. The darkness we observe nightly represents an apparent contradiction between basic astronomical assumptions and our most elementary observations. This is OLBERS paradox, named after the 19th century German astronomer Heinrich Olbers, though the problem was recognized by earlier thinkers, including Kepler and Halley. The paradox emerges from simple geometric reasoning. In an infinite universe evenly filled with stars, the number of stars at any given distance increases with the square of that distance. Meanwhile, the apparent brightness of each star decreases with the square of the distance. These effects exactly cancel out, meaning that shells of stars at increasing distances would each contribute equal amounts of light to Earth. With infinitely many such shells in an infinite universe, the night sky should be infinitely bright, resembling a continuous stellar surface in every direction, rather than isolated points of light against darkness. The controversy surrounding this paradox has evolved over centuries as our understanding of the universe transformed. Some early astronomers suggested interstellar dust might absorb the light from distant stars, explaining the darkness. Others proposed that stars might be arranged in ways that allowed most sight lines to miss them entirely. Modern cosmology offers more sophisticated resolutions, but disagreement persists about which factors most crucially explain the darkness and what the paradox reveals about our universe's structure. Consider the profound implications. The darkness between stars isn't merely an absence, but evidence, a visible manifestation of fundamental cosmic properties that shape our entire universe. What seems like nothing is actually telling us something crucial about cosmic history, structure, and destiny. The paradox transforms the commonplace experience of nighttime darkness into a window onto the universe's deepest characteristics and most basic parameters. Modern cosmology resolves the paradox primarily through three factors. First, the universe has a finite age, approximately 13.8 billion years, meaning we can only see stars within a limited light horizon, the distance light could travel since the universe began. Second, the universe is expanding, which redshifts light from distant sources, reducing its energy and shifting much of it outside the visible spectrum. Third, stars themselves have finite lifespans and weren't created simultaneously, further limiting their total contribution to night sky brightness. Some cosmologists emphasize the expanding universe as the primary resolution. Even in an infinite universe filled with stars, if those stars are rapidly moving away from each other, their light gets stretched to longer wavelengths. The most distant sources would be redshifted entirely out of the visible spectrum, appearing dark to human eyes despite actually bathing us in extremely long wavelength radiation. This perspective connects Olbers' paradox directly to the discovery of cosmic expansion and the birth of modern cosmology. Others focus on the universe's finite age as the key factor. Even if stars filled infinite space, we could only see those within roughly 13.8 billion light years, actually further due to expansion, but the principle remains. Beyond our observable universe, stars might shine brilliantly, but their light simply hasn't had time to reach us. From this perspective, the darkness between visible stars represents not empty space, but the light travel time limitation imposed by the universe's finite age, a direct visual manifestation of the Big Bang's recency. The paradox becomes even more fascinating when we consider its connection to cosmic structure. Modern observations reveal that matter isn't evenly distributed through space, but clumps into galaxies, clusters, and vast filaments separated by near-empty voids. This hierarchical clustering further reduces the total stellar surface area visible from any given point, contributing to the darkness. The paradox thus connects to questions about how gravity shaped our universe's evolution from its initially nearly uniform state to today's complex cosmic web. Some theorists connect Olbers' paradox to thermodynamic considerations involving entropy and the universe's energy distribution. The darkness of night represents a state of thermodynamic disequilibrium. If the universe were infinitely old and stars had been shining forever, their energy would have reached a uniform high-temperature equilibrium. The cool, dark sky we observe instead suggests a universe still evolving from a specific initial state toward increasing entropy, connecting the paradox to the fundamental arrow of time. The implications extend to astrobiology and the search for extraterrestrial intelligence. If the night sky were ablaze with stellar light, as Olbers' reasoning suggests, planets would be continuously illuminated from all directions at solar intensity. Life as we know it could never have evolved under such conditions. The dark sky isn't just an astronomical curiosity, but a prerequisite for complex life's development. Perhaps intelligent observers can only arise in universes where Olbers' paradox is resolved through properties like finite age or cosmic expansion. Modern observations in non-visible wavelengths reveal that the universe isn't entirely dark after all. The cosmic microwave background radiation, CMB, fills all of space with microwaves in a nearly perfect blackbody spectrum at 2.7 Kelvin. From a microwave perspective, the night sky glows nearly uniformly in all directions, a direct relic of the Big Bang itself. This background radiation represents an attenuated redshifted version of what was once the blindingly bright light of creation, connecting Olbers' paradox directly to cosmic origins. Some cosmologists find significance in how precisely the paradox's resolution balances multiple factors. If the universe were significantly older or expanded significantly slower, the night sky would indeed be brighter. If stars lived much longer or formed much earlier, more of their light would reach us. The dark sky we observe represents a specific relationship between cosmic age, expansion rate, and stellar evolution timescales, potentially offering clues about whether our universe's parameters are coincidental, physically necessary, or perhaps fine-tuned for observers like ourselves. The next time you gaze at the night sky, remember Olbers' paradox. Remember that the darkness between stars isn't merely an absence, but profound evidence about our universe's age, expansion, and structure. Remember that what seems like nothing is actually telling us something fundamental about cosmic history. Remember that in the apparent emptiness of space, we're actually observing direct evidence of the Big Bang, cosmic expansion, and the relatively recent emergence of stars and galaxies against the backdrop of time. The darkness of night, far from being a trivial observation, stands as one of the most accessible and yet profound cosmological clues available to naked human senses. A darkness that illuminates the very nature, history, and destiny of our universe. The GRUE paradox, when the future isn't like the past. All emeralds examined before time T are green, therefore all emeralds are green. This inference seems perfectly reasonable, a standard inductive generalization from observed cases to unobserved ones. But now consider an alternative hypothesis. All emeralds are GRUE, meaning they are green if examined before time T, but blue if examined after time T. The evidence we have, all emeralds examined before T being green, supports both hypotheses equally well. Why do we naturally prefer all emeralds are green over all emeralds are GRUE? This deceptively simple question is the GRUE paradox, introduced by philosopher Nelson Goodman in 1955, and it challenges our most fundamental assumptions about how we learn from experience. The paradox strikes at the heart of inductive reasoning, our ability to draw general conclusions from limited observations. When we observe that the sun has risen every day in recorded history, we confidently predict it will rise tomorrow. When scientists observe consistent patterns in nature, they formulate laws expected to hold indefinitely. But the GRUE hypothesis reminds us that our observations are equally consistent, with countless alternative patterns that diverge in the future. The preference for green over GRUE cannot be justified by the evidence alone. The controversy surrounding this paradox has divided philosophers of science, epistemologists, and cognitive scientists. Some argue that GRUE is an illegitimate predicate because it contains an arbitrary time reference, while others maintain both green and GRUE are equally legitimate from a logical perspective. Some suggest we prefer simpler hypotheses on pragmatic grounds, while others propose that certain predicates are more natural or entrenched in our conceptual systems. The paradox forces us to examine the hidden assumptions underlying our most basic inferential practices. Consider the profound implications. If evidence alone cannot distinguish between competing hypotheses about the future, what grounds our scientific predictions? Perhaps what we call laws of nature are merely patterns that have remained stable in our limited experience, but could change at any moment for no reason whatsoever. The paradox threatens to undermine the rational foundation of scientific inquiry itself, suggesting that our confidence in future predictions rests not on evidence, but on questionable metaphysical assumptions about nature's uniformity. The paradox becomes even more unsettling when we consider its relationship to the problem of induction, first articulated by David Hume. Hume argued that we have no rational justification for assuming the future will resemble the past. We simply have a psychological habit of expecting patterns to continue. The GRUE paradox gives this abstract concern concrete form, demonstrating precisely how our observations could be consistent with radically different futures. If Hume awakened us from our dogmatic slumber about induction, Goodman's GRUE paradox shows exactly how wide the chasm beneath our feet really is. Some philosophers propose that our preference for green over GRUE stems from the simplicity or naturalness of certain predicates. Green refers to a basic perceptual quality, while GRUE involves a complex time-index disjunction. But this raises deeper questions. What makes certain properties more natural than others? Is simplicity an indicator of truth or merely cognitive convenience? Perhaps our preference for simple predicates reflects limitations in human cognition rather than metaphysical facts about reality itself. Others suggest the paradox reveals assumptions about objective similarity relations in nature. We expect emeralds examined after tea to resemble those examined before tea because they share objective similarities, independent of when we observe them. But this merely pushes the question back. How do we know which similarities are objective rather than artifacts of our subjective categorization systems? The paradox suggests the distinction between natural and gerrymandered. Properties might itself be more psychological than metaphysical. The paradox extends into artificial intelligence and machine learning. AI systems learn patterns from training data to make predictions about future cases, essentially performing automated induction. But without built-in biases favoring certain patterns over others, these systems could equally well infer GRUE-like concepts consistent with training data, but diverging for future cases. The paradox suggests that successful inductive learning, whether by humans or machines, requires constraints beyond mere consistency with observations. Some cognitive scientists connect the paradox to how humans actually conceptualize the world. Developmental studies suggest children naturally favor certain property clusterings over others, showing inductive biases present from early age. Perhaps what philosophers call the problem of induction is solved in practice through evolutionarily shaped cognitive architecture that naturally favors certain conceptual schemes, those that tracked real patterns in our ancestral environments, over logically possible alternatives. The implications extend to statistical reasoning and scientific methodology. The paradox challenges the assumption that we can neutrally let the data speak for itself. Every inference from data to hypothesis involves implicit assumptions about which patterns are worth projecting. Scientific progress may require not just collecting observations, but developing better theories about which properties are genuinely explanatory, a process that cannot be reduced to mechanical rules of confirmation. Perhaps most profound is what the paradox reveals about the relationship between mind and world. Our inductive practices presuppose a deep alignment between human conceptual systems and nature's actual structure. We expect nature to be carved at joints our minds can readily discern, with future patterns continuing along lines we find intuitive. But this presumed harmony between thought and reality lacks independent justification, suggesting our confidence in induction involves an irreducibly metaphysical leap of faith. The next time you confidently predict future events based on past observations, whether expecting the sun to rise tomorrow, physical laws to remain constant, or human behavior to follow familiar patterns, remember the GRUE paradox. Remember that your evidence is equally consistent with countless bizarre alternatives, where these patterns shift in unexpected ways. Remember that your preference for natural continuing patterns over artificial, changing ones cannot be justified by evidence alone, but involves deep assumptions about reality's structure. Perhaps what separates rational prediction from superstition isn't the evidence itself, but how that evidence connects to our evolving understanding of nature's fundamental categories. The arrow paradox. How can anything ever move? Imagine an arrow in flight. At any given instant, the arrow occupies a single point in space, exactly its own length. At that instant, the arrow is neither moving to where it's going nor moving from where it's been. It's simply there, motionless, at that precise location. But if the arrow is motionless at every instant, and time consists entirely of instants, how can the arrow move at all? This is ZENO'S arrow paradox, an ancient puzzle that challenges our most fundamental understanding of motion, time, and change. The paradox emerges from the seemingly reasonable assumption that any period of time can be divided into distinct instants, infinitesimal moments where no change occurs. If we examine the arrow at any such instant, it occupies a specific location without moving. Yet motion requires changing position over time. The contradiction arises when we realize that summing infinitely many states of motionlessness shouldn't logically produce movement, yet obviously arrows do fly, and movement occurs. The controversy surrounding this paradox has persisted for over 2 millennia, dividing philosophers, physicists, and mathematicians. Some argue it reveals fundamental problems with conceptualizing time as composed of instantaneous moments. Others suggest it demonstrates the limitations of our intuitive understanding of infinity and continuity. Still others see it as exposing tensions between mathematical abstractions and physical reality. The paradox forces us to examine assumptions so basic we rarely question them. The nature of time itself, and how change occurs within it. Consider the profound implications. If we cannot reconcile the continuous flow of movement with time's apparently discrete structure, perhaps our entire conceptual framework for understanding physical change requires revision. The paradox suggests a fundamental mismatch between how we conceptualize reality mathematically and how reality actually unfolds. Perhaps motion isn't what we think it is. Perhaps time has properties we haven't grasped. Perhaps the relationship between instance and duration is more complex than simple aggregation. The standard mathematical resolution involves calculus and the limit concept. While the arrow occupies definite positions at specific instants, its velocity at each instant isn't zero, but is defined as the limit of the average velocity over increasingly small time intervals. Motion isn't found within any instant, but in the relationship between positions at different instants. This mathematical framework successfully models physical movement, but some philosophers argue it merely describes motion without resolving the conceptual paradox of how change emerges from changeless instants. Some philosophers propose that the paradox reveals problems with the very notion of instants as dimensionless points. Perhaps time isn't infinitely divisible, but consists of minimal temporal units with non-zero duration, chronons, the temporal equivalent of spatial atoms. Within each chronon, change occurs indivisibly. This discretization of time would prevent the infinite regress of temporal division that generates the paradox, though it introduces new conceptual and physical challenges. Others suggest the paradox stems from conflating different understandings of at an instant. In one sense, the arrow isn't moving at an instant, because movement requires duration. In another sense, the arrow has a state of motion at each instant, represented by its instantaneous velocity vector. The paradox dissolves when we recognize that being in motion isn't a property observable at a single instant, but a description of how position changes across multiple instants. Perhaps the instants themselves aren't primary, but derived from the continuous flow they segment. The paradox becomes even more fascinating when considered alongside modern physics. In quantum mechanics, particles don't have simultaneously definite positions and velocities, due to Heisenberg's uncertainty principle. The quantum world seems to resist the classical picture of objects following continuous trajectories through space, suggesting ZENO'S intuition that motion is problematic at the most fundamental level might have been remarkably prescient. Some theorists connect the paradox to deeper questions about the nature of time itself. Does time flow continuously, or does it progress through discrete ticks? Is the present moment real and substantial, or merely a conceptual boundary between past and future? Does time exist independently of events occurring within it? Or is it merely a relational property of changing systems? The arrow paradox suggests that our intuitive understanding of temporal progression may be fundamentally flawed or incomplete. The implications extend to philosophy of mind and the experience of consciousness. We perceive motion as continuous and flowing rather than as a series of static states. Does this reveal something about consciousness itself? Perhaps its fundamental temporality, or its ability to synthesize discrete inputs into continuous experience. The paradox raises the possibility that our subjective experience of continuous movement might be more fundamental than the mathematical decomposition of time into instants. Physicists studying the relationship between quantum mechanics and general relativity continue to grapple with questions about the fundamental nature of time and change. Some approaches to quantum gravity suggest space-time itself might be discrete at the Planck scale rather than continuous. Others propose that time might be an emergent property rather than a fundamental dimension. These cutting-edge theories often revisit questions first raised by Zeno's deceptively simple observation about a flying arrow. Some philosophers suggest the paradox reveals tensions between different ways of knowing, the mathematical abstraction that divides time into instantaneous slices versus the lived experience of duration and flow studied by phenomenologists. Perhaps complete understanding requires integrating these perspectives rather than reducing one to the other. The paradox might not demand solution but synthesis, recognizing that different conceptual frameworks capture different aspects of temporal reality. The next time you watch an object in motion, an arrow flying, a ball rolling, even your own hand moving through space, remember Zeno's arrow paradox. Remember that this seemingly straightforward phenomenon harbors profound conceptual challenges that have persisted for millennia. Remember that reconciling the mathematics of instantaneous states with the experienced reality of continuous movement continues to challenge our deepest thinkers. Perhaps what appears most obvious, that things move from place to place over time, actually conceals the deepest mysteries about the nature of reality itself. The flying arrow, suspended conceptually between the continuous flow we experience and the discrete instants we calculate, reminds us that even our most basic concepts, time, change, motion, might be approximations rather than final truths. Perhaps the paradox persists not because we haven't found the right solution, but because it exposes fundamental limitations in how minds evolved on human scales comprehend a reality that may operate according to principles we can model mathematically, but never fully intuit. The paradox of analysis. How can explanation add knowledge if it's just rephrasing? What happens when a philosopher claims a bachelor is an unmarried man? This seems uncontroversial, a simple definition, a clarification of terms. Yet this innocent statement harbors a profound puzzle. If bachelor and unmarried man mean exactly the same thing, then the statement merely says, an unmarried man is an unmarried man, a trivial tautology that teaches us nothing. But if these terms don't mean exactly the same thing, then the statement is either incorrect or incomplete as a definition. This is the paradox of analysis, first articulated by philosopher G.E. Moore in the early 20th century. How can analysis provide new knowledge if it merely replaces a concept with its equivalent? The paradox emerges whenever we attempt to analyze, explain, or define anything. Successful analysis should be both correct and informative. To be correct, the analysis must be identical in meaning to what's being analyzed. To be informative, it must tell us something we didn't already know. These requirements seem contradictory. If meanings are identical, no new information is provided. If new information is provided, meanings cannot be identical. Yet analytical explanations clearly do provide insights. The paradox challenges our understanding of how knowledge advances through the clarification of concepts. The controversy surrounding this paradox has divided philosophers of language, epistemologists, and cognitive scientists. Some argue it reveals fundamental problems with classical theories of meaning that equate a term's meaning with its definition. Others suggest it demonstrates distinctions between different types of knowledge. Perhaps we can know something without fully understanding it. Still others propose it exposes limitations in how we conceptualize identity and information. The paradox forces us to examine assumptions so basic we rarely question them, how concepts relate to one another, and how explanation generates understanding. Consider the profound implications. If all genuinely accurate analyses are uninformative tautologies, how does conceptual clarification ever advance knowledge? Yet mathematics, philosophy, and science clearly progress through increasingly precise analysis of concepts. The paradox suggests either that our understanding of meaning is fundamentally flawed, or that explanation operates through mechanisms more complex than mere conceptual equivalence. Either way, it challenges our basic understanding of how knowledge grows through clarification. Some philosophers propose resolving the paradox by distinguishing between different aspects of meaning. Perhaps bachelor and unmarried man have the same referential meaning. They pick out the same individuals in the world, but different cognitive meanings. They connect to different mental associations or conceptual networks. This would explain how a statement of equivalence could be both correct and informative. It links two conceptually distinct ways of thinking about the same reality. Others suggest the paradox reveals something profound about the structure of human understanding. Perhaps our knowledge isn't organized as a web of fully analyzed concepts, but as a system of partially understood ideas with varying degrees of clarity. Analysis moves concepts from implicit, intuitive understanding to explicit, articulated understanding without changing their essential content. The feeling of insight comes not from learning new facts, but from restructuring existing knowledge into more accessible patterns. The paradox becomes even more fascinating when considered in light of cognitive science research on conceptual processing. Studies suggest humans rarely represent concepts through explicit definitions, but rather through prototypes, exemplars, and fuzzy boundaries. Perhaps the classical view that equates meaning with definition fundamentally misrepresents how human concepts work. Analysis might provide genuine insight precisely because our initial grasp of concepts is partial, context-dependent, and implicit rather than through rigid definitions. Some philosophers connect the paradox to Wittgenstein's later work on family resemblances in language games. Perhaps many concepts resist classical analysis because they aren't unified by necessary and sufficient conditions, but by overlapping similarities, like members of a family. Game includes board games, card games, ball games, and video games, without any single feature common to all. Analysis provides insight by revealing these resemblances rather than by finding perfect definitions. The implications extend to artificial intelligence and knowledge representation. If human concepts resist formal definition in the way the paradox suggests, how should machines represent meaning? Neural network approaches that build distributed representations through exposure to examples might better capture human conceptual structures than classical symbolic approaches based on explicit definitions. The paradox might reveal not just a philosophical curiosity, but a fundamental challenge for creating machines that understand concepts as humans do. The paradox has practical consequences for education and explanation. If understanding doesn't come merely from learning definitions, but from restructuring existing knowledge, perhaps effective teaching requires connecting new ideas to students' current conceptual frameworks rather than presenting isolated definitions. The paradox suggests explanation works not by transmission of completely new information, but by helping reorganize what's already partially known. Some theorists propose that the paradox reveals the inherently contextual nature of explanation. The statement, "A bachelor is an unmarried man," might be informative in certain contexts, but trivial in others, depending on the background knowledge and current mental state of the person receiving the explanation. Perhaps there's no context-independent measure of informativeness, only explanations that work for particular individuals, with particular needs, at particular moments. The paradox challenges the classical picture of knowledge as a static collection of fully analyzed concepts. Perhaps understanding is always partial, always in progress. We grasp concepts well enough to use them competently, without exhausting their analytical potential. Each analysis reveals new aspects of meaning previously implicit, creating the perpetual possibility of insight without requiring completely new information. Knowledge might be less like a completed puzzle and more like an endlessly unfolding fractal, always containing further levels of structure to be revealed. The next time someone explains a concept, remember the paradox of analysis. Remember that explanation's power to generate insight conflicts with our simplistic models of meaning and information. Remember that understanding doesn't proceed through simple accumulation of definitions, but through complex restructuring of what's already partially known. Perhaps genuine learning isn't about acquiring entirely new information, but about seeing familiar concepts in unfamiliar relationships. A process that defies our traditional models of knowledge transmission, but captures the genuine experience of insight. The humble statement, "A bachelor is an unmarried man," contains within it not just a definition, but a profound question about the nature of understanding itself, how we move from vague familiarity to clear comprehension without paradox. The puzzle reminds us that even our most basic intellectual tools, definition, explanation, and analysis, harbor deep philosophical mysteries that touch the very foundations of how minds grasp meaning. The Raven Paradox. When irrelevant evidence supports a theory. Imagine trying to confirm the hypothesis that all ravens are black. Finding black ravens clearly supports this claim, but logically this is equivalent to the statement, all non-black things are non-ravens. By this logic, observing a white shoe confirms your hypothesis, just as much as observing a black raven. This is the Raven Paradox, first proposed by philosopher Carl Hempel in 1945. Why does finding a white shoe seem intuitively irrelevant to the hypothesis about ravens, when logically it provides exactly the same confirmatory evidence as finding a black raven? The paradox emerges from three principles that individually seem reasonable, but together generate counterintuitive results. First, logically equivalent statements are confirmed by the same evidence. Second, all ravens are black is logically equivalent to all non-black things are non-ravens. Third, observing something that matches our hypothesis, like a non-black non-raven, provides confirmatory evidence. Together, these principles suggest that observing literally anything that isn't a non-black raven, from white shoes to green leaves to purple dinosaur toys, confirms our theory about ravens' color. The controversy surrounding this paradox has divided philosophers of science, logicians, and statisticians for decades. Some accept the counterintuitive conclusion, arguing that observing non-black non-ravens does technically confirm the raven hypothesis, just to an extremely small degree. Others reject the paradox by challenging one of its premises, suggesting either that logical equivalence doesn't guarantee evidential equivalence, or that confirmation works differently than traditional accounts suggest. The paradox forces us to examine our most basic assumptions about how evidence relates to scientific theories. Consider the profound implications. If observing essentially anything can technically confirm a scientific hypothesis, might our intuitive understanding of evidence be fundamentally flawed? This isn't merely a philosopher's game, but strikes at the heart of scientific methodology. The paradox suggests either that logical analysis fails to capture how scientific confirmation actually works, or that our intuitive judgments about relevant evidence are mistaken. Either way, it challenges our understanding of how empirical observation connects to theoretical knowledge. Some philosophers propose resolving the paradox through the concept of background knowledge. We know there are far more non-black things than ravens in the world, so randomly observing a non-black non-raven provides negligible confirmation compared to observing a black raven. This approach accepts the paradoxical conclusion but explains why it doesn't match intuition. The confirmation exists, but is quantitatively insignificant, given what we already know about the relative frequencies of objects in the world. Others suggest the paradox reveals flaws in the traditional account of confirmation, as simple instances supporting generalizations. Perhaps confirmation depends not just on logical form, but on causal connections between evidence and hypotheses. While all ravens are black, and all non-black things are non-ravens are logically equivalent, they suggest different causal structures. The color of ravens might depend on biological factors, while the non-ravenous of non-black things has no unified causal explanation, making these observations qualitatively different as evidence. The paradox becomes especially interesting when considered alongside modern scientific practice. Scientists rarely test universal generalizations directly, but work with statistical patterns, causal models, and theoretical frameworks. Perhaps the paradox primarily reveals limitations in overly simplistic logical models of scientific reasoning, rather than genuine problems with scientific methodology itself. It might demonstrate why scientists rely on background theories and experimental design, rather than mere observation of random instances. Some statisticians connect the paradox to Bayesian probability theory, suggesting that different prior probability distributions explain why observing a white shoe and a black raven have dramatically different confirmatory power. If ravens are relatively rare compared to non-black things, then observing a black raven increases the probability of all ravens are black, much more significantly than observing a random non-black non-raven. The paradox might reflect failure to account for these probabilistic nuances, rather than a fundamental problem with confirmation. The implications extend beyond philosophy of science into artificial intelligence and machine learning. How should AI systems weigh evidence when forming and testing hypotheses? Does the paradox suggest limitations for computational approaches to scientific discovery based on formal logic alone? Perhaps effective scientific reasoning requires not just logical manipulation, but background knowledge about the structure of the world that goes beyond what's explicitly stated in the hypothesis being tested. Some philosophers suggest the paradox reveals problems with how we naturally conceptualize categories and properties. We think of raven as a natural category with causal unity, while non-black things seems gerrymandered and heterogeneous. Perhaps this reflects a deep feature of human cognition. We naturally organize knowledge around causally unified categories, rather than treating all logically possible classifications as equally meaningful. The paradox might expose tensions between logical formalisms and how human minds naturally organize empirical knowledge. Modern philosophers of science often approach the paradox through the lens of scientific practice, rather than pure logic. Scientists typically don't randomly sample objects from the world, but design careful experiments testing specific causal mechanisms. They work within theoretical frameworks that suggest which observations would be surprising or informative, rather than treating all logically relevant observations equally. The paradox might primarily demonstrate the limitations of overly simplified models of scientific method, rather than exposing genuine problems with scientific reasoning. The next time you consider what counts as evidence for a scientific theory, remember the Raven paradox. Remember that logical analysis alone suggests even seemingly irrelevant observations technically support general hypotheses. Remember that what makes evidence compelling might not be captured by simple logical relationships, but involves background knowledge, causal understanding, and theoretical context. Perhaps scientific reasoning isn't reducible to formal logic, but relies on sophisticated cognitive frameworks for assessing relevance, significance, and surprise. The white shoe's peculiar relationship to black ravens reveals that evidence, confirmation, and scientific reasoning are far more complex than simple logical formulae suggest. It reminds us that the gap between abstract logical principles and practical scientific methods might be larger than we initially assume, and that this gap itself deserves careful investigation if we hope to understand how science actually advances knowledge about the world. The twin paradox. When time becomes relative. Imagine identical twins. One remains on Earth while the other boards a spacecraft and travels at near light speed to a distant star before returning home. According to Einstein's special relativity, time passes more slowly for objects moving at high velocities, a phenomenon called time dilation. When the traveling twin returns, she has aged significantly less than her Earth-bound sibling. But wait. From the traveling twin's perspective, couldn't she consider herself stationary while Earth moved away at high speed and then returned? Shouldn't the Earth-bound twin be the one who ages less? This apparent contradiction is the twin paradox, a thought experiment that challenges our deepest intuitions about time and simultaneity. The paradox emerges directly from Einstein's special relativity, which establishes that time passes differently for observers, moving relative to each other. The faster the relative motion, the more pronounced the time difference becomes. This isn't mere theory. Atomic clocks on high-speed aircraft register time differences exactly as predicted by relativity. GPS satellites must constantly adjust for relativistic effects to maintain accuracy. The counterintuitive nature of the paradox doesn't stem from questionable physics, but from the difficulty our Earth-evolved brains have comprehending a universe where time itself is malleable. The controversy surrounding this paradox has fascinated physicists, philosophers, and science fiction enthusiasts for over a century. Some initially claimed it revealed a fundamental contradiction in relativity theory itself. Others argued it demonstrated the impossibility of faster-than-light travel. Most physicists now agree the paradox has a clear resolution within relativity, but disagreement persists about which aspects of the theory most clearly resolve it, and how best to explain the asymmetry between the twins' experiences. Consider the profound implications. If time itself is relative rather than absolute, what does this suggest about the nature of reality? If two observers can legitimately disagree about whether events are simultaneous or about how much time passes between events, then objective reality cannot be as simple as our intuitions suggest. The paradox forces us to confront the possibility that the universal now we instinctively believe in simply doesn't exist in any objective sense. The standard resolution focuses on the asymmetry of acceleration. While both twins can legitimately claim to be stationary during the constant velocity portions of the journey, with the other twin moving away, Only the space traveler experiences acceleration when changing direction. This acceleration breaks the symmetry between the twins' reference frames, making their situations physically distinguishable. The traveling twin passes through multiple inertial reference frames during her journey, while the earthbound twin remains in a single inertial frame throughout. Some physicists prefer to resolve the paradox through the concept of world lines, the paths objects trace through four-dimensional space-time. The earthbound twin's world line is relatively straight, while the traveling twin's world line curves significantly to form a loop back to Earth. These different paths through space-time naturally result in different elapsed proper times, the time experienced by each twin, just as different paths between 2 points on Earth's surface can have different lengths. The paradox becomes even more fascinating when we consider its implications for cosmic expansion. Galaxies receding from us at significant fractions of light speed should experience time dilation from our perspective. Yet from their perspective, we're the ones receding at high speed. This cosmic scale twin paradox raises profound questions about time's passage throughout the universe and whether age differences between distant regions of space-time have physical meaning, given the impossibility of reuniting these cosmic twins. Some philosophers connect the paradox to broader questions about personal identity and consciousness. If the traveling twin ages significantly less, perhaps returning decades or even centuries younger than her sibling, what does this suggest about the relationship between physical time and subjective experience? If consciousness is linked to brain processes that occur in time, how would subjective experience differ for beings moving at different velocities through space-time? The implications extend to potential future technologies. If humans eventually develop near light-speed travel capabilities, time dilation would create profound social disruptions. Space travelers might return to find generations have passed on Earth, with all their contemporaries long dead. Would societies develop around different time streams, some aging normally on planets, others living at different rates as they travel between stars? The paradox suggests interstellar civilization might face temporal divides far more significant than mere spatial separation. Some theorists have proposed more exotic resolutions involving general relativity's treatment of gravity as space-time curvature. From this perspective, acceleration creates local gravitational effects that directly cause the time dilation experienced by the traveling twin. This approach unifies the twin paradox with other relativistic effects like gravitational time dilation, where clocks run slower in stronger gravitational fields, an effect measurably present even between different floors of the same building on Earth. The paradox has practical implications for potential future space exploration. Human missions to Mars already must account for relativistic effects, though the differences amount to only milliseconds. But a hypothetical mission to a nearby star system at significant fractions of light speed would create noticeable age differences between mission personnel and Earth-based support teams. Space agencies developing long-term exploration strategies must incorporate these temporal considerations alongside more conventional engineering challenges. Perhaps most profound is what the paradox reveals about the nature of time itself. Far from being the absolute universal flow that our intuition suggests, time emerges as an intrinsic aspect of space-time that varies with relative motion and gravitational fields. What we experience as the steady passage of time is revealed as a parochial perspective, a local approximation that breaks down under conditions far from our evolutionary environment. The paradox suggests time isn't something that exists independently of the physical universe, but is deeply woven into its fabric. The next time you synchronize watches with someone, remember the twin paradox. Remember that this synchronization is only approximate, that in principle, your watches would drift apart if one of you moved at high speed relative to the other. Remember that the universal now we instinctively believe in is an illusion born of our shared low-velocity existence on Earth's surface. Remember that time itself is more fluid and contextual than our Earth-evolved intuitions can comfortably grasp. The twin paradox isn't merely a curious thought experiment, but a window into the true nature of our universe. A reality where time and space interweave into a single unified space-time, where simultaneity is relative, and where the passage of time depends not just on clocks, but on how those clocks move through the cosmic fabric. In challenging our most fundamental intuitions about time, the paradox reveals a universe far stranger and more magnificent than our ancestors could have imagined. The lottery paradox. Why rationality sometimes requires believing contradictions. Imagine a fair lottery with 1 million tickets. For any particular ticket, the probability of winning is 1 in a million, so vanishingly small that it seems perfectly rational to believe this ticket will lose. Since this reasoning applies equally to every ticket, rationality seems to demand believing each individual ticket will lose. Yet you also know with certainty that some ticket must win. This creates a paradoxical situation where rationality seems to require simultaneously believing each ticket will lose and some ticket will win, a flat contradiction. This is the lottery paradox, first formulated by philosopher Henry Keiberg in 1961, and it challenges our most basic understanding of rational belief. The paradox emerges from 3 principles that individually seem reasonable, but jointly lead to contradiction. First, it's rational to believe propositions that are highly probable. Second, rational belief should be closed under conjunction. If you rationally believe A and rationally believe B, you should rationally believe A and B together. Third, you shouldn't rationally believe contradictions. The lottery scenario forces these principles into conflict. High probability justifies believing each ticket will lose. Conjunction combines these beliefs, but the combined belief contradicts the certainty that some ticket will win. The controversy surrounding this paradox has divided epistemologists, decision theorists, and cognitive scientists. Some reject the first principle, arguing that high probability alone never justifies outright belief, only degrees of confidence. Others reject closure under conjunction, suggesting rational belief doesn't combine like logical operators. Still, others embrace the paradoxical conclusion, proposing that rational belief systems might sometimes contain controlled contradictions. The paradox forces us to examine assumptions so basic we rarely question them, how belief, probability, and rationality interconnect. Consider the profound implications. If rationality sometimes leads to contradictory beliefs, perhaps our entire conception of rationality requires revision. This isn't merely an abstract puzzle, but directly impacts how we should form beliefs under uncertainty in everyday life. From medical diagnoses to financial planning to climate predictions, we constantly face situations where probabilistic reasoning suggests beliefs that, when combined, generate contradictions. The paradox suggests either that probability doesn't translate directly into justified belief, or that rational belief follows different rules than classical logic. Some philosophers propose resolving the paradox by distinguishing between degrees of belief and outright belief. Perhaps outright belief requires certainty or justification beyond mere statistical probability. We might have 99.9999% confidence each ticket will lose without making the leap to outright belief. This preserves logical consistency, but raises new questions. What threshold separates confidence from belief? Why maintain this distinction if high confidence serves the same practical purposes as belief? Others suggest the paradox reveals that rational belief doesn't always combine through simple conjunction. Perhaps believing ticket 1 will lose and ticket 2 will lose doesn't automatically justify believing ticket 1 and ticket 2 will both lose. This approach preserves the connection between high probability and rational belief, but challenges traditional assumptions about the logical structure of belief systems. It suggests belief aggregation follows rules more complex than classical logic, perhaps reflecting cognitive limitations or pragmatic constraints. The paradox becomes especially interesting when considered alongside other epistemological puzzles, like the preface paradox, where an author believes each statement in their book but also believes the book contains errors, and the SORITES paradox, where small incremental steps lead from clearly true to clearly false statements. Together, these suggest the relationship between probability, rational justification, and logical consistency might be fundamentally more complex than traditional philosophical accounts suggest. Some decision theorists connect the paradox to practical reasoning, arguing that rational belief should be understood through its role in decision-making rather than abstract logical properties. From this perspective, believing each ticket will lose might be perfectly rational for practical purposes. You wouldn't bet significant resources on any particular ticket winning, despite the theoretical inconsistency when these beliefs are combined. Perhaps rationality concerns effective action in the world rather than maintaining perfectly consistent belief systems. The implications extend to artificial intelligence and computational approaches to uncertainty. How should AI systems form beliefs based on probabilistic evidence? The paradox suggests that simply converting high probabilities into beliefs risks generating inconsistent belief systems. Modern approaches like Bayesian networks avoid explicit beliefs in favor of probability distributions, perhaps reflecting the paradox's lesson that categorical belief formation from probabilities inevitably risks inconsistency. Some cognitive scientists suggest the paradox reveals important features of human cognition. Perhaps humans don't actually maintain perfectly consistent belief systems, but operate with context-dependent beliefs that shift based on which questions we're currently considering. When thinking about individual tickets, we naturally believe each will lose. When thinking about the lottery overall, we believe some ticket will win. This contextual shifting might represent not a flaw, but an adaptive feature of minds operating under computational constraints. The paradox connects to broader questions about ideal rationality versus bounded rationality. Classically, perfect rationality requires logical consistency among all beliefs, but maintaining global consistency requires computational resources that exceed human capabilities. Perhaps rational belief for bounded agents necessarily tolerates certain kinds of local inconsistency as the price of effective functioning with limited cognitive resources. The paradox might reveal not a problem with human rationality, but a feature of any intelligent system operating under real-world constraints. The next time you confidently believe an improbable event won't happen, that your plane won't crash, that you won't be struck by lightning, that a specific investment won't fail, remember the lottery paradox. Remember that extending this reasonable confidence to every similar case creates tension with the certainty that some such events must occur. Remember that rational belief might not follow the clean, logical structure we intuitively assume, but involves complex negotiations between probability, practical reasoning, and cognitive limitations. The lottery ticket's lesson extends far beyond games of chance to the very foundations of how we should form and maintain beliefs in an uncertain world. It suggests that perfect consistency might be neither achievable nor necessary for rational functioning, and that the gap between ideal rationality and effective thinking under real-world constraints deserves serious consideration in how we understand both human and artificial intelligence. ZENO'S paradoxes. The impossibility of motion. Imagine you want to cross a room. Before you can reach the other side, you must first reach the halfway point. Before reaching the halfway point, you must reach the quarter-way point. Before that, the eighth-way point. This pattern continues infinitely. Before reaching any point, you must always reach a prior point. Since there are infinitely many points to traverse, and even the smallest journey requires infinite steps, motion itself should be impossible. Yet clearly, we move. Welcome to ZENO'S paradox, an ancient Greek puzzle that has confounded philosophers and mathematicians for nearly 2,500 years. Zeno of Elea, a pre-Socratic philosopher, developed several variations of this paradox around 450 BCE. The most famous, known as the dichotomy, describes the infinite divisions outlined above. Another, Achilles and the tortoise, proposes that the swift Achilles can never overtake a tortoise given a head start, because whenever Achilles reaches the tortoise's previous position, the tortoise will have moved to a new position. Though each gap gets smaller, Achilles must traverse infinitely many gaps, making the overtaking seemingly impossible. Yet in reality, Achilles would easily pass the tortoise. The controversy surrounding these paradoxes extends far beyond ancient philosophy. They strike at the heart of our understanding of infinity, continuity, and the nature of physical reality itself. Some philosophers have interpreted Zeno's paradoxes as demonstrating the illusory nature of motion and change. Perhaps reality is actually static, and our perception of movement merely an illusion. Others see the paradoxes as revealing fundamental problems with how we conceptualize space, time, and infinity. Consider the profound implications. If even the simplest movement requires traversing infinite points, how is motion possible at all? Does this suggest that physical space cannot be infinitely divisible? Or perhaps time itself cannot be broken down into infinitesimal instants? The questions raised by Zeno's simple thought experiments have shaped mathematical and philosophical thinking for millennia, influencing fields from calculus to quantum physics. Modern mathematics offers one resolution through the concept of convergent infinite series. While it's true that crossing the room requires passing through infinitely many points, the sum of these infinitely many distances is finite. The series 1/2 plus 1/4 plus 1/8 plus 1/16 plus converges to exactly 1, despite having infinitely many terms. This suggests that completing infinitely many tasks is possible if each successive task takes proportionally less time, allowing Achilles to overtake the tortoise in a finite time span. Yet this mathematical solution wasn't available in Zeno's time. The formal theory of limits in infinite series wouldn't be developed until the 17th century with the invention of calculus. For over 2,000 years, these paradoxes remained profoundly troubling to thinkers grappling with the concept of infinity. Even today, some philosophers argue that mathematical solutions merely describe the paradox without truly resolving its deeper metaphysical implications. The paradoxes become even more complex when we consider quantum mechanics. At the quantum level, space may not be infinitely divisible, but instead composed of minimal units called Planck lengths. If space is granular rather than continuous, perhaps Zeno's infinite divisions are physically impossible rather than merely mathematically resolvable. Could ancient Greek philosophy have anticipated a fundamental truth about physical reality that physics would only discover millennia later? Some philosophers suggest the paradoxes reveal problems with our understanding of time rather than space. If we conceive of time as composed of indivisible moments rather than an infinitely divisible continuum, the paradoxes dissolve. This perspective aligns intriguingly with certain interpretations of quantum mechanics, where time might be quantized just as other physical properties are. Perhaps Zeno was right all along. Continuous motion, as we intuitively understand it, might indeed be impossible at the most fundamental level of reality. Others focus on the paradox's implications for the nature of infinity itself. Mathematicians now distinguish between potential infinity, an endless process that's never complete, and actual infinity, a completed infinite totality. Zeno's paradoxes may demonstrate the difficulty of applying actual infinity to physical processes that unfold in time. The infinite divisions of space may exist as a mathematical abstraction, but physical movement may involve only potential infinity, an endless possibility of further division that's never actually completed. The paradoxes extend beyond pure philosophy into cognitive science. How does our brain represent continuous motion? Research suggests we don't perceive motion as a series of infinitesimal steps, but as a continuous flow. Perhaps Zeno's paradoxes reveal the limitations of analytical thinking when applied to processes our brains evolved to perceive synthetically. The conflict might not be in reality itself, but in the mismatch between our analytical and perceptual systems. From ancient Greece to modern physics labs, Zeno's paradoxes have forced us to reconsider our most basic assumptions about reality. Is space infinitely divisible? Is time continuous? Can a process with infinitely many steps be completed? These questions echo from Zeno's time to our own, transforming from philosophical curiosities into pressing scientific inquiries as we probe deeper into the fundamental structure of the universe. Some mathematicians find beauty in how the paradoxes anticipated calculus by over 2 millennia. The mathematical framework for handling infinity and infinitesimals, the foundation of calculus, provides elegant solutions to puzzles that once seemed logically impenetrable. Perhaps Zeno's greatest contribution wasn't proving motion impossible, but inadvertently setting humanity on a path toward deeper mathematical understanding of the infinite. Physicists studying the nature of space-time continue to find relevance in these ancient thought experiments. As we develop theories attempting to reconcile quantum mechanics with general relativity, fundamental questions about the continuous versus discrete nature of space and time remain open. Loop quantum gravity, string theory, and other approaches suggest different answers to questions, first posed by a Greek philosopher nearly 2,500 years ago. The next time you cross a room, consider ZENO'S paradox. Remember that your simple movement involves traversing potentially infinite points in space, completing what ancient philosophers considered logically impossible. Remember that the elegant mathematics resolving the paradox took humanity thousands of years to develop. Remember that even now, at the cutting edge of theoretical physics, we're still grappling with the fundamental nature of space, time, and motion that ZENO'S paradoxes call into question. What ZENO showed wasn't that motion is impossible, but that our intuitive understanding of infinity, continuity, and physical reality contains profound contradictions that continue to challenge our deepest theories about the universe. The arrow flies, Achilles overtakes the tortoise, and we cross rooms every day. Yet the philosophical questions raised by these simple facts remain as provocative now as they were in ancient Greece. The paradox of the heap. SORITES paradox. When does quantity become quality? Imagine a heap of sand containing 10,000 grains. Now remove one grain. Is it still a heap? Of course. Remove another grain. Still a heap? Yes. Continue this process. When does it stop being a heap? If removing a single grain never transforms a heap into a non-heap, then even one grain of sand, or 0 grains, would still constitute a heap. Yet intuitively, we know a single grain is not a heap. This is the SORITES paradox, also known as the paradox of the heap, and it reveals a fundamental problem with how human language deals with vague predicates. The term SORITES comes from the Greek word for heap, but the paradox extends far beyond sand piles. Consider, when does a person become old? When does a collection of houses become a city? When does a musical group become loud? When does adding wealth make someone rich? In each case, no single incremental change seems sufficient to transform one category into another, yet the transformation undeniably occurs. The paradox highlights the troubling imprecision at the heart of concepts we use daily without a second thought. The controversy surrounding this paradox has divided philosophers into competing camps. Some embrace the view that vague terms like heap have no precise boundaries. Their meanings are inherently fuzzy, with borderline cases that can't be definitely classified. Others argue that precise boundaries must exist for terms to be meaningful, but these boundaries are unknown to us or may shift contextually. Still others propose that classical logic itself, with its strict true-false dichotomy, may be inadequate for representing vague concepts. Consider the profound implications. If language cannot precisely capture gradual transformations, how reliable is it for describing reality? When medical diagnoses like hypertension or legal categories like adult are defined by sharp numerical boundaries, 140 over 90 millimeters of mercury, 18 years, they impose artificial precision on naturally continuous variables. The paradox suggests such distinctions, while practically useful, might be conceptually problematic, failing to reflect the continuous nature of the phenomena they describe. Some philosophers propose fuzzy logic as a solution, replacing classical true-false distinctions with degrees of truth. In this framework, a collection might be 90% a heap or 30% a heap, with truth values gradually transitioning as grains are removed. While mathematically elegant, this approach raises new questions. Do these percentages themselves have sharp boundaries? Is there a precise moment when something transitions from being 70% a heap to 69% a heap? The paradox seems to reappear at a deeper level, Others suggest epistemic approaches, maintaining that precise boundaries exist but are fundamentally unknowable to us. Perhaps there is an exact number of grains that constitutes a heap, but human cognitive limitations prevent us from identifying it. This preserves classical logic, but at the cost of positing invisible boundaries that seem suspiciously convenient and untestable. How could such precise natural boundaries exist for social constructs like rich or famous that are human inventions? The paradox becomes even more complex when we consider its relationship to personal identity. You lose cells and replace them with new ones constantly. At what point, if ever, would you become a different person through this gradual replacement? The ancient ship of Theseus paradox asks a similar question about objects whose parts are gradually replaced. These aren't merely abstract puzzles, but questions that touch on fundamental issues of identity, persistence, and change. Some cognitive scientists suggest the paradox reveals something important about how human categorization works. Rather than using necessary and sufficient conditions with sharp boundaries, humans might categorize objects based on similarity to prototypical examples. A typical heap has many grains, but as we move away from this prototype, category membership becomes increasingly unclear. This explains why borderline cases are so troubling. They exist in the fuzzy boundary region where similarity to the prototype is neither clearly sufficient nor clearly insufficient. Legal systems struggle with SORITES-type problems constantly. When does reasonable force become excessive? When does negligence become recklessness? When does intoxication invalidate consent? Lawmakers and judges attempt to draw bright lines through naturally continuous spectra, necessarily creating arbitrary boundaries. The paradox suggests this arbitrariness isn't a fixable flaw, but an inevitable consequence of applying discrete categories to continuous reality. The implications extend to ethical questions as well. The classic trolley problem asks whether it's permissible to divert a trolley to kill one person instead of 5. But what if the numbers were different? Is it permissible to kill 1 to save 2, 3, 4? At what precise ratio does the moral calculation flip? The SORITES structure of many ethical dilemmas suggests that moral principles often lack the precise boundaries we might wish for when making difficult decisions. Modern science faces similar challenges. When does a collection of cells become an organism? When does a group of humans become a society? When does climate change become catastrophic? Scientific definitions attempt to impose precision, but the underlying phenomena often resist sharp categorization. The paradox suggests this isn't merely a limitation of current knowledge, but a fundamental challenge in mapping discrete language onto continuous reality. Some philosophers connect the paradox to broader questions about reductionism. If removing single grains never transforms a heap into a non-heap, yet the transformation occurs, this suggests certain properties aren't reducible to the simple accumulation of their constituents. Perhaps heapness is an emergent property that appears only when certain thresholds are crossed, similar to how consciousness might emerge from neural activity, despite no single neuron being conscious. The paradox might reveal something profound about how complex properties relate to their simpler components. The next time you use words like tall, rich, old, or cold, remember the paradox of the heap. Remember that the seemingly sharp categories through which we navigate the world mask continuous spectra that defy precise boundaries. Remember that the gap between our discrete linguistic tools and the continuous nature of reality creates inevitable paradoxes that no amount of definition refining can fully resolve. The heap of sand teaches us that language itself contains inherent limitations, not because we haven't found the right definitions yet, but because the fundamental structure of language, with its discrete categories, may be inherently inadequate for capturing the continuous gradations of reality. The paradox isn't in the world, but in the gap between the world and our tools for describing it. Simpson's paradox. When aggregating data reverses the truth, imagine a medical study comparing two treatments for kidney stones. Treatment A shows a 78% success rate, while treatment B shows only 73%. The evidence clearly favors treatment A, right? But when researchers separate patients by stone size, something bizarre happens. For small stones, treatment B outperforms A, 93% versus 87%. And for large stones, treatment B again outperforms A, 73% versus 69%. How can treatment B be superior in every subgroup yet inferior overall? This statistical mindbender is Simpson's paradox, where a trend that appears in different groups reverses when those groups are combined. This isn't merely a mathematical curiosity. This exact scenario occurred in a real 1986 study published in the British Medical Journal. The explanation? Treatment B was disproportionately used on more difficult cases, large stones, creating an illusion of inferior performance when the data was aggregated. But within each comparable group, treatment B was actually superior. The paradox demonstrates how data that appears straightforward can hide a completely different, even opposite, reality beneath its surface. The controversy surrounding this paradox extends far beyond medical research into policy decisions, social science, and ethics. Some statisticians argue that disaggregated data, separated by relevant subgroups, always provides the true picture. Others maintain that which perspective is correct depends entirely on the specific question being asked. Still others suggest the paradox reveals a fundamental limitation in how we interpret causality from statistical correlations. When a pattern reverses upon grouping, which version represents reality? Consider the profound implications. How many medical treatments have been incorrectly judged superior or inferior because researchers failed to account for this paradox? How many social policies have been implemented based on aggregate statistics that reversed when properly segmented? The paradox suggests our statistical evidence might be systematically misleading us, not through deliberate manipulation, but through mathematical properties inherent in how we analyze data. One of the most disturbing examples emerged in the 1970s when UC Berkeley was investigated for gender bias in graduate admissions. The aggregate data showed men were admitted at significantly higher rates than women, suggesting systematic discrimination. But when researchers broke down the data by department, they discovered women actually had slightly higher admission rates in most individual departments. The paradox occurred because women disproportionately applied to competitive departments with lower overall acceptance rates. What initially appeared to be gender bias was revealed as a more complex pattern of gendered application preferences. This doesn't mean discrimination doesn't exist. It absolutely does. But it demonstrates how Simpson's paradox can obscure the true nature of disparities. Similar reversals have been observed in studies of racial disparities in capital punishment, income inequality trends, and educational outcomes. In each case, the aggregate picture told one story, while the disaggregated data revealed something substantially different. The paradox forces us to ask, which story is true, and how do we decide? Some social scientists suggest the paradox reveals the limitations of purely statistical approaches to complex social phenomena. Numbers alone, without contextual understanding of causal mechanisms, can lead to fundamentally wrong conclusions, not because the mathematics is incorrect, but because the interpretation fails to account for lurking variables that create the reversal. Perhaps human judgment and domain expertise remain essential even in our age of big data and algorithmic decision-making. The paradox becomes even more troubling when we consider how it affects public discourse. Media headlines highlight aggregate statistics without delving into the more complex disaggregated picture. Politicians cite overall trends that might reverse when properly segmented. Even when no one is deliberately lying, Simpson's paradox can lead everyone, including experts, to fundamentally misunderstand what the data is actually saying. Some researchers propose that causal analysis rather than mere statistical correlation is the only way to avoid the paradox's trap. By understanding the causal structure behind the data, which variables influence others, and how, we can determine which grouping provides the most accurate picture. But this requires moving beyond pure statistics into theoretical frameworks that statistics alone cannot provide. The paradox highlights the limits of a purely data-driven approach, divorced from causal reasoning. The implications extend into machine learning and artificial intelligence. Algorithms trained on aggregate data might learn patterns that reverse in important subgroups, potentially leading to harmful decisions when deployed in the real world. Some researchers worry that as automated systems increasingly make decisions affecting human lives, Simpson's paradox might create systematic blind spots where algorithms consistently make wrong choices despite being correctly trained on the available data. The paradox also raises profound questions about scientific methodology. The replication crisis in psychology and medicine has revealed how many established findings fail to reproduce in new studies. Could Simpson's paradox be partially responsible? If small, unidentified subgroup differences exist, findings that appear robust in one population might systematically reverse in another, not because the original study was flawed, but because the aggregation concealed crucial heterogeneity. Perhaps most unsettling is the paradox's implications for how we understand truth itself in a data-driven society. If the same data set can simultaneously support contradictory conclusions, depending on how it's grouped, and both analyses are mathematically correct, then what constitutes the truth of the matter? The paradox suggests that data rarely speaks for itself. It always requires interpretation, and different interpretations can lead to fundamentally different understandings of the same reality. The next time you see a headline citing a statistical trend, whether in medicine, economics, social policy, or any other field, remember Simpson's paradox. Remember that the aggregate picture might be hiding its exact opposite when properly disaggregated. Remember that what appears to be a clear signal might transform into a completely different message when viewed through the appropriate lens. The truth in data isn't always what it first appears to be, not because of deception, but because of the mathematics of aggregation itself. Simpson's paradox doesn't mean we should distrust statistics. Quite the opposite. It means we should demand more sophisticated statistical analysis that accounts for relevant subgroups and causal structures. It means recognizing that summary statistics, while useful, can conceal as much as they reveal. In a world increasingly driven by data, understanding this paradox isn't just a mathematical curiosity. It's essential for discerning what our numbers are really telling us about reality. The Doomsday Argument, Are we living at the end of humanity? Imagine placing yourself randomly among all humans who will ever live. Some must be born early in history, others in the middle, and some toward the end of humanity's existence. Basic probability suggests you're more likely to be somewhere in the middle of this distribution than at either extreme. But here's the disturbing conclusion. If you're in the middle, and approximately 100 billion humans have already lived, then the total number of humans who will ever exist might be around 200 billion, suggesting human extinction could occur within just a few centuries. This is the Doomsday argument, a probabilistic reasoning exercise first formally presented by astrophysicist Brandon Carter in 1983. Though similar ideas have emerged independently multiple times, the argument doesn't predict a specific apocalyptic mechanism, nuclear war, pandemic, climate catastrophe, or artificial intelligence gone rogue, but rather suggests that purely based on statistical reasoning, we're likely closer to humanity's end than its beginning. The controversy surrounding this argument has divided philosophers, cosmologists, and probabilists. Some accept its logic but dispute its assumptions. Others reject the application of self-locating probability to species longevity. Still others accept its conclusions but differ on their implications. The argument's disturbing elegance forces us to confront not just humanity's mortality, but the proper application of probability to our place in history. Consider the profound implications. If we're truly near the end of humanity's timeline, efforts to ensure long-term human survival might be futile. Colonizing other planets, developing sustainable technologies, or uploading consciousness to digital substrates might merely delay the inevitable by decades or centuries, rather than securing humanity's existence for millions of years. Conservation efforts for distant future generations might be preserving resources for people who will never exist. Some critics attack the argument's assumption that you should consider yourself randomly selected from all humans who will ever live. Perhaps the very fact that you're alive during this crucial period in human development, with technological capabilities to either destroy ourselves or ensure our long-term survival, suggests your birth timing isn't random, but specifically located at a pivotal moment. This self-selection bias might invalidate the random placement assumption. Others suggest the argument overlooks the possibility of post-human future. Perhaps biological humans will evolve or transform into something no longer recognizable as human, invalidating the counting of all humans who will ever live. If humanity transitions into a post-human phase with trillions of digital consciousness instances, the calculation changes dramatically. Your birth in the late biological phase would then be expected rather than improbably early. The argument becomes even more complex when we consider observation selection effects. The Doomsday argument could only be formulated by observers who have reached a certain level of scientific sophistication, which inevitably occurs after billions of humans have already lived. This creates a potential bias. We couldn't have made this observation much earlier in human history, so perhaps our temporal location isn't as informative as the argument suggests. Some philosophers connect the argument to anthropic reasoning more broadly, the principle that our observations are necessarily constrained by the requirements for our existence as observers. Similar reasoning leads to the fine-tuning argument. Why are cosmic constants precisely calibrated to allow life? And the simulation argument. Are we living in a computer simulation? The Doomsday argument might reveal less about humanity's future than about the limits of applying probability to our own existence. The implications for existential risk assessment are particularly troubling. If the argument is valid, it suggests we should update our probability estimates for human extinction upward, not based on any specific threat assessment, but purely on statistical grounds. This could either motivate greater urgency in addressing existential risks or foster a fatalistic acceptance that humanity's end is statistically likely regardless of our efforts. Critics point out that the argument contains a potential self-defeating element. If widely accepted, it might motivate extraordinary efforts to ensure human survival, potentially invalidating its conclusion. Conversely, if it breeds fatalism that reduces survival efforts, it might become a self-fulfilling prophecy. This reflexive quality, where the argument's acceptance affects the reality it attempts to predict, creates a logical peculiarity that some philosophers find deeply problematic. Population ethics adds another layer of complexity. If humanity survives into the distant future, eventually spreading throughout the galaxy, trillions or quadrillions of humans might eventually live. If this long future is possible, the expected value of preserving human civilization becomes almost incalculably large, potentially outweighing the doomsday argument's statistical reasoning. Even a small probability of an extremely long human future might justify massive investment in survival, regardless of the argument's conclusion. Some philosophers suggest the argument reveals less about humanity's future than about the limitations of certain types of probabilistic reasoning. When applied to unique entities like all humans who will ever exist, traditional statistical methods might break down in ways that generate seemingly valid but ultimately misleading conclusions. Perhaps the argument is mathematically sound but pragmatically useless, valid within its restrictive assumptions, but inapplicable to actual decision-making. The argument shares structural similarities with other probabilistic puzzles, like the Sleeping Beauty problem and the Fermi paradox. All involve self-locating uncertainty. Uncertainty about where, when you exist, relative to some larger reference class. The persistent controversies surrounding these problems suggest we haven't fully resolved how to apply probability to questions of where we stand in relation to larger collections that include ourselves. The next time you consider humanity's long-term future, planning for climate adaptation centuries ahead, designing nuclear waste warnings intended to last millennia, or contemplating interstellar travel, remember the doomsday argument. Remember that pure statistical reasoning suggests we might be fooling ourselves about humanity's longevity. Remember that our existence at this particular moment in history might not be the cosmic coincidence it appears, but rather a predictable location near the temporal midpoint of humanity's story. Whether the argument ultimately proves sound or flawed, it forces us to confront uncomfortable questions about our species' mortality and our cosmic significance. Are we the ancestors of a galactic civilization that will thrive for millions of years? Or are we among the last generations before some terminal catastrophe? The mathematics suggests the latter is more probable, even as our hopes and efforts aim toward the former. Perhaps the most profound aspect of the doomsday argument is how it places cold statistical reasoning in direct conflict with our deepest aspirations for humanity's future. The faint young sun paradox. How was Earth not a frozen wasteland? 4 billion years ago, our sun burned approximately 30% dimmer than it does today. According to basic climate models, this reduced solar output should have left Earth completely frozen. A solid ball of ice with surface temperatures hovering around -30 degrees Celsius, -22 degrees Fahrenheit. Yet geological evidence tells us liquid water existed on Earth's surface at that time. Life not only survived, but began to flourish. This contradiction between established physics and geological evidence is the faint young sun paradox, first identified by astronomers Carl Sagan and George Mullen in 1972. The controversy surrounds a deceptively simple question: how did Earth maintain temperatures suitable for liquid water and life when the sun provided insufficient energy to keep the planet from freezing? This isn't a minor discrepancy. The energy gap is massive, equivalent to Earth intercepting only 70% of the solar radiation it receives today. Without some extraordinary compensating mechanism, our planet should have been locked in a global ice age, so severe that life might never have emerged. Scientists have proposed numerous solutions, each with passionate advocates and critics. Some suggest Earth's atmosphere contains significantly higher concentrations of greenhouse gases, particularly carbon dioxide, methane, and ammonia, creating a powerful greenhouse effect that trapped the limited solar heat. Others propose that Earth's albedo reflectiveness was lower, allowing the planet to absorb more of the sun's energy despite its reduced output. Still others suggest more exotic mechanisms involving cosmic rays, different cloud formations, or even fundamental errors in our understanding of stellar evolution. Consider the profound implications. If we can't fully explain Earth's climate under well-understood conditions from its past, how confident can we be in predicting its future under human-induced climate change? The paradox suggests our climate models might be missing crucial feedback mechanisms or overlooking important variables. Understanding exactly how Earth maintained its habitability under a faint young sun could reveal critical insights about climate stability and planetary habitability that have direct relevance to our current climate crisis. The paradox becomes even more intriguing when we consider its astrobiological implications. If maintaining liquid water under a faint young sun required extremely specific atmospheric conditions, this might suggest habitable planets are exceedingly rare. Conversely, if multiple mechanisms could produce the necessary warming, this might imply habitability is more robust than we thought. Our understanding of how common life might be throughout the universe hinges partly on resolving this ancient terrestrial paradox. Some climatologists argue that extreme greenhouse effects from methane and carbon dioxide levels, hundreds of times higher than present-day concentrations, could explain the necessary warming. But this solution creates new problems. Such high CO2 levels should leave distinctive geological signatures that haven't been consistently found, and methane typically breaks down quickly in atmospheres containing oxygen. The greenhouse solution remains controversial, despite its initial appeal. Others focus on cloud behavior, suggesting that reduced cloud cover during this period could have significantly decreased Earth's albedo, allowing more of the sun's limited energy to be absorbed. Some propose that different patterns of air circulation created by the supercontinent Walbra, which existed during this time, might have reduced cloud formation. Yet questions remain about whether cloud coverage changes alone could provide sufficient additional warming. The paradox becomes even more complex when we consider that it coincides with periods when Earth experienced several severe glaciations. This suggests the climate system was teetering on the edge of global freezing, despite whatever warming mechanisms were operating. How did Earth maintain this delicate balance, occasionally slipping into glacial periods, but always recovering? The paradox might reveal fundamental climate-stabilizing mechanisms that prevented permanent glaciation, despite the energy deficit. Some geologists suggest the paradox might be partially resolved by challenging the geological evidence itself. Perhaps liquid water existed only in limited regions, near volcanic activity, or in equatorial zones. while most of the planet remained frozen. Others propose that the chemical composition of ancient oceans, with different salinity and mineral content, might have allowed liquid water to exist at lower temperatures than modern oceans. These approaches don't eliminate the paradox, but might reduce its magnitude. Astronomers have proposed more radical solutions, including questioning whether our understanding of stellar evolution is accurate. Maybe the young sun wasn't actually as faint as standard models suggest. Perhaps it rotated more rapidly, generating stronger solar winds that interacted with Earth's magnetic field to produce additional heating. While these hypotheses remain minority views, they highlight how the paradox challenges assumptions across multiple scientific disciplines. The implications extend to our search for habitable exoplanets. Many potentially habitable worlds orbit red dwarf stars, which remain at relatively constant luminosity for billions of years, avoiding the faint young star phase entirely. Does this make them more promising candidates for life than solar-type stars? Or did Earth's climate adaptations to a strengthening sun create evolutionary pressures that were crucial for complex life's development? The paradox might suggest which stellar types are most likely to host life-bearing worlds. Perhaps most fascinating is the possibility that life itself helped resolve the paradox. Early organisms might have produced methane or reduced Earth's reflectivity through their presence in oceans, creating a biological feedback loop that maintained habitable conditions. This Gaia hypothesis approach suggests life doesn't merely adapt to planetary conditions, but actively shapes them, creating a coupled system where biology and geology evolve together to maintain habitability. The next time you read about climate models or the search for habitable exoplanets, remember the faint young sun paradox. Remember that despite all our advances in understanding Earth's climate, fundamental mysteries remain about how our planet maintained habitable conditions during its early history. Remember that these ancient puzzles have direct relevance to contemporary questions about climate stability, planetary habitability, and the prevalence of life in the universe. The paradox reminds us of both the remarkable resilience of Earth's climate system and the limitations in our understanding of it. 4 billion years ago, through mechanisms we still haven't fully unraveled, our planet somehow maintained liquid water and nurtured emerging life, despite receiving inadequate solar energy, a cosmic mystery whose resolution might hold the key to understanding both Earth's climate future and the potential for life on countless worlds beyond our own. BURIDAN'S ass, the paradox of perfect rationality. Picture a perfectly rational donkey standing exactly midway between two identical bales of hay. Both bales are the same size, the same distance away, equally fresh and equally appetizing. The donkey, being perfectly rational, has no reason to prefer one bale over the other. Without any basis for choice, unable to decide which way to turn, the perfectly logical animal starves to death between two abundant sources of nourishment. This is Buridan's ass, a paradox named after 14th century French philosopher John Buridan, though the thought experiment predates him. At first glance, it might seem merely amusing, a caricature of overthinking. But beneath its simple surface lies a profound challenge to how we understand rationality, decision-making, and the very nature of choice itself. The controversy surrounding this paradox strikes at the heart of competing philosophical traditions. Determinists argue that without a sufficient reason to choose one option over another, no choice can be made. The ass's paralysis is the only logical outcome. Defenders of free will counter that the ability to make arbitrary choices in the face of perfect symmetry is precisely what defines agency. A truly rational being would simply pick one, recognizing that any choice is better than none. Consider the implications for artificial intelligence. As we build increasingly sophisticated decision-making algorithms, Buridan's paradox takes on new urgency. A perfectly rational AI facing exactly balanced options might enter a processing loop, unable to find the decisive factor that doesn't exist. Some AI researchers believe this necessitates introducing randomness into decision-making systems, a deliberate irrationality to prevent decision paralysis. Is true intelligence, then, necessarily imperfect? The paradox extends to human psychology as well. Studies show that excessive options can produce decision paralysis in consumers. People faced with 24 jam varieties often buy none, while those offered just 6 are more likely to make a purchase. When options are too numerous and too similar, the mental cost of evaluation outweighs the benefit of perfect selection. We become information age incarnations of BURIDAN'S ass, starving amid abundance because we cannot decide. Some philosophers argue the paradox reveals a fundamental misunderstanding of rationality itself. True rationality isn't the pursuit of the optimal choice, but the recognition that in cases of perfect symmetry, the cost of deliberation exceeds the marginal benefit of selecting the right option. A truly rational agent would recognize when differences are negligible and make an arbitrary choice to avoid paralysis. Perhaps rationality isn't about making the best choice, but about knowing when further deliberation is itself irrational. The paradox becomes even more complex when we consider its implications for moral philosophy. Imagine a moral dilemma where 2 options are exactly balanced in terms of ethical outcomes. Can a perfectly moral agent make a choice? Some argue that truly identical moral choices are impossible in the real world, that sufficient analysis would always reveal relevant differences. Others suggest that moral reasoning, like other forms of rationality, must ultimately include mechanisms for breaking symmetry when perfect balance occurs. Quantum mechanics offers another perspective on Buridan's paradox. At the quantum level, perfect symmetry doesn't lead to paralysis, but to superposition, existing in multiple states simultaneously until observation forces a collapse into one state. Perhaps Buridan's ass, if it operated on quantum principles, would approach both bales simultaneously, existing in a superposition of states until some random quantum fluctuation broke the symmetry. Does quantum indeterminacy offer an escape from the paralysis of perfect rationality? The paradox challenges our understanding of causality itself. What causes a choice when all causal factors are perfectly balanced? If every event requires a sufficient cause, how can any decision emerge from perfect equilibrium? Some philosophers suggest this reveals a fundamental incompleteness in our causal models of reality, that something beyond mere causation must explain how choices emerge from symmetrical situations. Economic theories of rational choice face similar challenges. The Homo economicus model assumes individuals always make rational utility-maximizing decisions. But what happens when utilities are exactly equal? Game theory usually resolves this by introducing mixed strategies and probability, effectively adding a randomization element to decision-making. Is perfect rationality, paradoxically, dependent on controlled irrationality? The paradox becomes particularly poignant when applied to existential choices. Many life decisions, which career to pursue, whether to have children, where to live, involve options with incommensurable values that cannot be reduced to a single metric for comparison. How do we make choices when the options are not just similar, but qualitatively different in ways that defy comparison? Perhaps existential choices reveal the limits of rationality itself, requiring leaps of faith rather than calculations of utility. Some philosophers suggest that emotion serves as the necessary symmetry breaker in human decision-making. When reason reaches equilibrium, subtle emotional preferences tip the scales. Without emotion, they argue, human decision-making would succumb to Buridan's paralysis far more often. Is emotion, then, not an impediment to rationality, but its necessary complement? Others point to randomness as the essential escape from decision paralysis. Many organisms appear to incorporate stochastic elements in their behavior, particularly when searching for resources. This random walk strategy prevents getting stuck in local optima or decision loops. Perhaps evolution has selected for mechanisms that specifically prevent Buridan-type paralysis through controlled randomness. The paradox extends to social choice theory as well. When groups must make collective decisions and preferences are evenly balanced, how does consensus emerge? Arrow's impossibility theorem suggests that no voting system can satisfy all reasonable fairness criteria simultaneously. Perhaps social decision-making inevitably involves arbitrary elements when collective preferences approach equilibrium. When facing difficult choices in your own life, remember Buridan's ass. Remember that perfect rationality without symmetry-breaking mechanisms leads to paralysis, not wisdom. Remember that sometimes any choice is better than no choice, that deliberation has costs as well as benefits, and that recognizing when differences are negligible is itself a form of rationality. The starving donkey between two bales of hay isn't just a philosophical curiosity. It's a warning about the limitations of pure reason, divorced from mechanisms for breaking symmetry when perfect balance occurs. In a world of abundant options and limited time, knowing when to stop calculating and simply choose might be the highest form of rationality after all. The grandfather paradox. When causality eats itself, you step into a time machine, destination set, your grandfather's youth, decades before your parents' birth. In your pocket, a loaded gun. Your mission seems simple, if grim. Kill your grandfather before he meets your grandmother. You find him easily enough, take aim, and fire. But wait, if you succeed, your parent would never be born. And if your parent doesn't exist, neither can you. Yet here you stand, finger on the trigger. If you don't exist, who is holding the gun? Who traveled back in time? Who is about to pull the trigger? Welcome to the grandfather paradox, where causality ties itself in knots and logic crashes against the brick wall of contradiction. This isn't merely a thought experiment for science fiction enthusiasts. It strikes at the heart of how we understand time, reality, and the fundamental structure of our universe. The controversy surrounding this paradox has split physicists and philosophers into competing camps. Some maintain that the paradox proves time travel to the past is fundamentally impossible, a logical impossibility that no technology, regardless of its sophistication, could ever overcome. The laws of physics, they argue, must somehow forbid any scenario that could create such causal loops. Time may be more rigid than our intuitions suggest. Others propose more exotic solutions. Perhaps attempting to change the past automatically generates a parallel universe. A new timeline branches from the moment of intervention. In this view, you could indeed kill your grandfather. But the man you murder isn't actually your grandfather. He's an identical version in a newly created reality. Your original timeline continues to exist unaltered. You haven't changed your past. You've created an alternate future. Perhaps the most unsettling proposition is that reality itself would somehow prevent any attempt to change history. Your gun would jam, you'd miss, or some coincidence would preserve the timeline. This Novikov self-consistency principle suggests time is less like a line and more like a four-dimensional block where past, present, and future already coexist. Your attempts to change the past were always part of that past. The universe, in essence, conspires against paradox. Consider this disturbing thought. What if we're all living in the aftermath of countless failed time travel attempts? What if our reality is simply the only version where the paradoxes were resolved? Every inexplicable coincidence, every strange turn of fortune could be reality desperately maintaining its logical consistency against temporal intruders. The grandfather paradox extends beyond academic curiosity when we consider its implications for free will. If the future already exists in some sense, if time is a dimension we move through rather than create, then perhaps our choices are as fixed as our past. Our sense of agency might be as illusory as our perception of the present moment. Quantum mechanics adds another layer of complexity. At the quantum level, cause and effect become blurred, with particles appearing to influence each other across time. Some interpretations suggest quantum entanglement might actually operate backward in time, with future measurements affecting past states. If reality at its most fundamental level allows for such temporal weirdness, perhaps macroscopic paradoxes aren't so impossible after all. The paradox becomes even more profound when we consider our own lives. If you could go back and prevent your worst mistake, would you? Even if it meant the person you are today would cease to exist? Every hardship shapes us. Every wrong turn leads to unexpected discoveries. In erasing our errors, we might erase the very experiences that define us. We become unwitting participants in our own grandfather paradoxes, our present selves murdering the conditions that created them. Some philosophers have suggested that consciousness itself involves a kind of temporal paradox. Our awareness of the present moment requires processing that takes time, meaning we're perpetually experiencing a past we reconstruct rather than the actual present. Our entire subjective experience might be a grand exercise in retroactive continuity, our brains constantly rewriting history to maintain the illusion of a seamless narrative. The grandfather paradox doesn't just question whether time travel is possible. It questions whether time as we understand it exists at all. It forces us to confront the possibility that our most fundamental intuitions about causality, sequence, and existence might be profoundly limited, useful approximations rather than ultimate truths. Perhaps time is not a river flowing in one direction, but an ocean where all moments coexist. Perhaps cause and effect are less like links in a chain and more like patterns in a tapestry already woven. Perhaps the universe is stranger than we can imagine, and the loaded gun aimed at our grandfather has already both fired and not fired in the timeless reality beneath our temporal perceptions. What if the only reason you exist is because you will eventually break the laws of physics? What if your very birth is a cosmic contradiction waiting to resolve itself? The grandfather paradox isn't just about time travel. It's about whether reality itself allows contradictions to exist, and what happens when the foundation of reason starts to crumble. The paradox of tolerance. Must freedom permit its own destruction? In a perfectly tolerant society, should intolerance itself be tolerated? If yes, intolerant groups may eventually dominate and destroy tolerance altogether. If no, then the society was never truly tolerant to begin with. This is the paradox of tolerance, first described by philosopher Karl Popper in 1945, and it strikes at the heart of liberal democracy's most cherished values. Imagine a society dedicated to maximum freedom of speech, belief, and assembly. Such a society would seemingly allow even for groups advocating the elimination of these very freedoms. Yet if these groups succeed, tolerance disappears. If they're suppressed, the society has compromised its own principles. Either way, absolute tolerance appears self-defeating. This isn't merely a philosophical thought experiment. It's the central dilemma facing liberal democracies confronted with extremist movements that use democratic freedoms to pursue anti-democratic ends. The controversy surrounding this paradox has divided philosophers, legal scholars, and political theorists for generations. Some argue that a truly tolerant society must defend itself against existential threats, even if this means restricting certain expressions of intolerance. Others contend that any limitation on speech or belief, however hateful, betrays the very principles that distinguish liberal democracy from authoritarianism. The paradox forces us to question whether unlimited tolerance is not just impractical, but conceptually incoherent. Popper himself proposed one resolution. We should claim that any movement preaching intolerance places itself outside the law, and we should consider incitement to intolerance and persecution as criminal. Yet this raises troubling questions. Who defines intolerance? Where precisely is the line between criticism and incitement? What safeguards prevent those in power from labeling political opponents intolerant to silence legitimate dissent? The paradox transforms from abstract philosophy into concrete policy challenges that democracies must navigate daily. The implications extend beyond speech to all fundamental freedoms. Should a tolerant society allow intolerant religious practices? Should it permit intolerant political parties to participate in elections? Should educational institutions provide platforms for speakers with intolerant views? Each question forces us to balance competing values and interests without clear guidelines for resolution. The paradox constantly resurfaces because it reflects a genuine tension within liberal democratic principles themselves. Some philosophers suggest distinguishing between first-order tolerance of ideas and practices and second-order tolerance of intolerance itself. Perhaps a coherent liberal democracy can be maximally tolerant at the first order while strategically intolerant at the second order, allowing wide latitude for diverse views while drawing firm boundaries against those who would eliminate diversity. Critics counter that this distinction often proves impossible to implement without subjective judgments that inevitably reflect the biases of those in power. The paradox becomes even more complex when we consider its international dimensions. Should tolerant nations tolerate intolerant regimes as legitimate global actors? Should they respect cultural differences that include intolerant practices? The tension between universal human rights and cultural relativism mirrors the internal paradox that liberal societies face. Respect for difference seems to require accepting some practices that themselves deny respect for difference. Historical examples provide sobering context. The Weimar Republic's tolerance toward the Nazi Party, which openly advocated dismantling democratic institutions, led to history's most catastrophic failure of democracy. Yet overzealous suppression of dissent during the McCarthy era in America demonstrates how easily the prohibition of intolerance can become a tool for political repression. The paradox isn't merely theoretical. It has shaped global history through cycles of excessive tolerance and excessive restriction. Some legal scholars propose that the solution lies in distinguishing between expressing intolerant ideas, which should be protected, and acting on those ideas in ways that harm others, which should be prohibited. This speech-action distinction seems elegant, but it blurs in practice. When does hateful rhetoric become incitement? When does organizational membership become conspiracy? The paradox resurfaces in these granular distinctions, defying clean resolution. Perhaps the most disturbing implication is that perfect tolerance may be not merely impractical but logically impossible, just as Gödel's incompleteness theorems proved that no mathematical system can be both complete and consistent. The paradox of tolerance suggests that no society can be both perfectly tolerant and self-sustaining. Liberal democracy may require accepting certain inherent contradictions, not as flaws, but as necessary features of a system balancing competing values. Modern social media platforms face this paradox daily, struggling to balance free expression against the spread of hateful content. Should they tolerate users who advocate intolerance? Their content moderation policies represent practical attempts to resolve the paradox. Yet each decision inevitably attracts criticism from those who prioritize either maximum freedom or maximum protection from harmful speech. The paradox proves persistently irresolvable, even with teams of experts and sophisticated algorithms attempting to navigate it. Some philosophers suggest that tolerance itself has been misunderstood. Perhaps tolerance was never meant to be an absolute value, but rather an instrumental one, valued not for itself, but for facilitating human flourishing and peaceful coexistence. From this perspective, the paradox dissolves. Tolerance extends precisely as far as it serves these broader goals, and no further. Intolerance that threatens these goals receives no protection precisely because it undermines tolerance's purpose. Others propose that the resolution lies in democratic processes themselves. Perhaps what matters isn't finding the perfect abstract balance between tolerance and self-preservation, but rather ensuring robust democratic procedures for continually negotiating this balance as circumstances change. The paradox may have no permanent resolution, but rather requires ongoing democratic deliberation, responsive to evolving threats and values. The next time you hear calls to ban certain speech or limit certain freedoms in democracy's defense, remember the paradox of tolerance. Remember that the tension between absolute freedom and necessary restriction isn't a bug in liberal democracy, but a feature, a necessary complexity in any system that values both liberty and equality, both diversity and unity, both individual rights and collective security. Remember that simple answers to this paradox have historically led to either vulnerability to extremism or descent into authoritarianism. The perfectly tolerant society remains an impossible ideal, not because we lack sufficient commitment, but because the concept itself contains an irreducible contradiction. Yet perhaps acknowledging this impossibility doesn't diminish liberal democracy, but enriches it, transforming it from a rigid ideology into an ongoing conversation about how best to balance competing values in an imperfect world. The paradox of tolerance doesn't defeat democracy, it defines it. The liar paradox, when truth destroys itself. This statement is false. 4 simple words that have shattered logical systems, crashed computer programs, and haunted philosophers for over 2,500 years. Read it again. If the statement is true, then it must be false, as it claims. But if it's false, then its claim about being false must be wrong, making it true. Each conclusion contradicts itself, creating an infinite logical loop that can never resolve. The liar paradox first emerged in ancient Greece, attributed to Epimenides of Crete, who allegedly stated, "All Cretans are liars." As a Cretan himself, his statement creates a similar self-reference problem. But this isn't merely an ancient curiosity. This paradox strikes at the foundation of mathematics, computer science, linguistics, and even our understanding of truth itself. The controversy surrounding this paradox has divided logicians into competing camps. Some believe it reveals fundamental flaws in our reasoning systems, while others claim it's merely a linguistic trick with no deeper meaning. Yet its implications reach far beyond academic debate. When our legal systems, computer code, scientific methods, and philosophical frameworks all rely on classical logic, can we afford to ignore its contradictions? In the early 20th century, the paradox took center stage in the foundations of mathematics. Bertrand Russell discovered a version of the liar paradox lurking in set theory, the mathematical framework upon which arithmetic itself is built. His famous Russell's paradox asked whether the set of all sets that don't contain themselves contains itself. Like the liar paradox, either answer leads to contradiction. This discovery triggered a crisis in mathematics, forcing a complete rebuilding of its logical foundations. The impact on computer science has been equally profound. Self-referential statements can create infinite loops that crash programs, or worse, create security vulnerabilities. The entire field of computational logic must carefully guard against these paradoxes. Gödelian attacks, cyber attacks based on logical paradoxes, represent an emerging threat to AI systems. A sufficiently advanced artificial intelligence encountering certain forms of the liar paradox might enter unstable states with unpredictable consequences. Some philosophers argue the paradox reveals truth itself isn't binary, but exists in states beyond true and false, just as quantum particles exist in states beyond simply here or there. Others suggest truth is hierarchical, with meta-languages required to discuss the truth of statements in object languages. These approaches multiply the complexity of logical systems, creating towers of increasingly abstract languages. The paradox becomes even more unsettling when we consider its implications for consciousness and self-reference. Our minds constantly generate self-referential thoughts. We think about our own thinking, judge our own judgments, doubt our own doubts. If self-reference inevitably leads to paradox, what does this suggest about the logical coherence of consciousness itself? Some cognitive scientists propose that our sense of self emerges precisely from these strange loops of self-reference, with paradox not as a bug, but as a feature of consciousness. Every truth you believe contains assumptions that cannot be proven within their own system. Mathematician Kurt Gödel demonstrated that any logical system complex enough to describe basic arithmetic must contain statements that are true but unprovable within that system. His incompleteness theorems, inspired partly by the liar paradox, shattered the dream of creating a perfectly complete and consistent mathematical foundation. Your certainties are built on logical quicksand, with bedrock truth forever out of reach. Modern approaches to the paradox include Alfred Tarski's hierarchy of languages, which forbids a language from containing its own truth predicates, and Saul Kripke's theory of truth gaps, which allows statements to lack truth values entirely. Others have developed multi-valued logics, where statements can be partially true, neither true nor false, or simultaneously both. Each solution patches the hole in classical logic, but creates new questions about the nature of truth itself. The paradox extends beyond formal logic into everyday reasoning. Consider this variation. The next statement is true. The previous statement is false. Neither statement directly refers to itself, yet together they form an unresolvable contradiction. Our legal systems face similar issues with self-referential laws and circular definitions. Constitutional paradoxes can emerge when laws refer to their own validity, or when legal powers are recursively defined. Perhaps most profound is how this paradox challenges our understanding of knowledge itself. If our logical systems inevitably contain contradictions, can we ever claim certainty about anything? Every truth claim rests on logical frameworks that, at their foundations, may harbor unresolvable paradoxes. The liar paradox doesn't just question specific statements. It questions whether human reasoning can ever fully capture reality. Some philosophers suggest the paradox actually reveals the limitations of language rather than logic. Perhaps certain concepts simply cannot be expressed without contradiction, just as certain mathematical concepts cannot be expressed in first-order logic. The fault may lie not in our reasoning, but in the constraints of how we must express that reasoning. The next time you find yourself absolutely certain of a truth, remember the liar paradox. Remember that even our most carefully constructed logical systems contain statements that break those very systems. Remember that truth itself might be stranger and more elusive than we imagine, neither fully capturable in our languages nor fully expressible in our logics. Perhaps truth, like quantum reality, is fundamentally probabilistic, paradoxical, and stranger than classical thinking can accommodate. This statement is false. 4 words that continue to challenge our deepest assumptions about knowledge, truth, and the limits of human understanding.